the link. I think we'll need to reshare that.
This call is now being recorded.
Okay. I think we'll need to reshare that link so that they can. Okay. Yeah. We'll send it on WhatsApp. Okay, so good morning, everyone. So first of all, if you have not finished your sum check, if you have finished your sum check, your non-interactive sum check, just wave your hand. You have finished your non-interactive sum check. Okay, so we're expected to move into GKR today. Okay. So we're going to be looking into GKR today. Moving into GKR should mean that we've finished with some check, so that we can focus on GKR. So the link should be out by tomorrow, max, right? So that we can submit our link, our GitHub link. And maybe after submitting the link, all of us should just pack our bags. Or just pack your bag,
Eviction or jump?
Maybe.
Yeah.
Maybe.
We're kicking some people out soon.
Actually. So from Wednesday, everybody just pack your bag. Hopefully by Sunday. You get.
So far, right now, they are not here. There are some people that are supposed to be here, they are not here, and they have not gone anywhere in their position.
And they are not following up. And they are not asking questions. So what are you doing on site?
To have people here.
Right? So initially, when we started, what did I say? I said you use your hand and kick yourself out, right? And that's literally what's going to happen. Some people will use their hand to kick themselves out. We're not the ones that will send you home. You will use your hand to send yourself home. Right? But it doesn't end there. You must not be here to know ZK, right? You can still know ZK from home. But there's the advantage of being here, right? Connecting with people and being able to learn these things fast. So if you're here and you're not taking advantage of that, then it's better you just go home where you have time, right? Focus on yourself and learning ZK. Okay, so I think let's just Is the screen size okay, or should I zoom in a bit more? Let me show that this thing still has my screen. Okay, so how many of us have heard of buying a Boolean circuit before? A Boolean circuit. Okay. Anybody can just tell us what you think a Boolean circuit is.
Yeah, so it's logical gates like connected together, and or not connected to like many more.
Exactly. Huh? Something gates, right? So we can think of a Boolean circuit as maybe a connection of logic gates, right? So a gate takes, say we have a gate, right? Let's say we have an OR gate, right? It takes in two inputs, gives out an output. Right. So if this is 0 and 0, what will be the output? 0. Okay. So still an OR gate. If this is 0 and 1, it will be a 1, right? Okay, let me draw the truth table. Let me use AB. Right. So 0, 0 give us 0, right? 0, 1 give us 1. So if this is 1, 0, what are we going to get? 1. And if this is 1, 1, 1. Okay. So this is the truth table associated with this OR gate, right? Do we all agree? Okay. So just as we have like OR gates, we have AND gates, right? We have NOT gates. Which other gates do we have? We have NAND. We have XOR. Yeah. So there are a lot of them, right? Yeah. So basically, the computer works with Boolean gates, right? Where 1 means on and 0 means off. So electricity is just passing through a lot of gates, and they are feeding into other gates, right? Which feeds into other gates. Like if we have these gates that takes in two values, the output of the gate can feed into another gate, right?
Yeah.
Do we agree or not?
Yeah, but it's not showing.
Oh, it's not showing.
It's a lag.
Network. Yes, I need to be verifying this. What happened the other day now? Not repeat itself. Okay. Right. So we have these two gates. Let's say they take A and B. Then the output C. Right. But this output we feed it into another gate. Right. Let's say this is, or let's say this is A, B, C, D. These are the inputs. AB is going into this gate to give us C, right? Sorry. Let's say E. Right. CD is going into this gate to give us F. And then the output of this circuit will be G. So we have a set of inputs. We can think of this as the input layer, right? And then each gate processes those inputs and gives us outputs, right? Those outputs, we feed them into another gate and it gives us outputs. So it just continues going like that. right? So this is kind of like, so it's still possible that a gate can take in more than two inputs, right? Let's say a gate, but that will not be like a Boolean gate again, right? Because a Boolean gate takes in two values. Okay, so does the whole circuit thing like make sense? Like the Boolean circuit? Huh? It's making sense, right? So actually what we're going to be dealing with is arithmetic circuits, right? Still the idea of the Boolean circuit, but now instead of a gate to be and or, it's going to be like an arithmetic operation. You get? So we can have like an addition gate, we can have a multiplication gate, right? So we take in inputs and we spit out an output. So for this addition gate, if we take in 5 and 2, what will be our output? 7, right? If we say the output is 8, is this gate valid? It's not, right? For our multiplication gate, if we take in 10 and 5, what do you expect as our output? 50, right? If we say this is 25, is this gate valid? It's not valid, right? Because this gate is a multiplication gate, and the multiplication gate has like kind of like constrained what happens to the two inputs. Does that make sense? Okay. So basically, like, we can think of any computation as a set of gates. Okay.
Okay, so you said that the computer was built, we know that computer was built on Boolean circuit. So why are we now using arithmetic circuit? Wouldn't it have been better to just use Boolean?
To use Boolean circuits. It would have been better to use Boolean circuits, right? But if we are using Boolean circuits, say we want to do 5 plus 2 with a Boolean circuit, what will it look like? It's going to be very complex, right? Because we are going to need to convert 5 to binary, right? We convert 2 also to binary, and then like we have a gate that will take in each of those bits, right, and perform operations on them. So it's kind of like going to be like a much bigger circuit. Does that make sense?
But this arithmetic circuit now is like a layer of abstraction that we are using for ZK, but then at the end of the day, computer still converts everything down to like a Boolean.
Yeah, like basically computer works with binary, right? So anyhow we want to represent a program, anyhow it is, the computer will still compile it down to binary, right? Okay, so like all this makes sense, right? And the whole gate stuff makes sense too. So let's say we want to evaluate a polynomial, right? How much should give us a polynomial? A univariate polynomial. 2x squared plus 2x plus 2x plus 1. We want to evaluate this polynomial, right? How can we represent this as a set of, or as a circuit, basically? Like a set of arithmetic gates. Okay.
Square, operation, and everything.
Okay. So, what will it look like?
X dot
X
X.
dot x. Okay. Should be equal to x squared. Right? Okay.
And 2 times x squared.
Maybe we can use another.
Okay.
Yeah, x squared.
2x squared.
Yeah.
Right?
Then 2 times X.
You also have, yeah.
2 times x should be equal to 2x.
You add.
No, okay, so that's
You add. No, it should be. Oh, yeah,
Two
we'll
x
add
squared
2x squared
plus
plus
2x.
Okay, so 2x squared plus,
2x.
Plus.
yeah, plus 2x, right? Let's say it will still give us 2x squared plus 2x, right? Like the output will still give us 2x squared
Yes.
plus 2x.
Add the
And then we can now add 1, right? Let's just add 1.
This is what the solution constant like.
Yeah. Okay, we can as well say let this be u, right? And then u plus 1, right? Will be equal to 2x squared plus 2x plus 1. Does it make sense? Okay, so this was like basically generating the constraints for each gate. Let's now represent it graphically, right? So for this, what is it going to look like? We'll have one multiplication gate, right? That takes in x and x, right? Then the result
output, yeah.
goes into what?
Another multiplication
Another multiplication gate.
and two
And the other side is 2. The other input.
Which other? This
The
side,
other input,
Yeah.
yeah.
two.
Can we put another symbol?
another symbol.
Maybe Y or
Oh,
let's just
no, that's times
Okay, okay. Let's use
asterisk.
asterisk. This one or dot,
Or dot, yeah.
Wow.
right? It's okay.
Yeah.
Okay. Let's go. Let's go with asterisk. Okay. Okay, so two fits into this gate.
Yeah.
Are we sure?
Yeah. So that's 2x squared.
Okay, so this.
That's x squared.
Okay, so this is 2x squared. So the output of this gate is x squared, right? Then we feed in 2. So this should be 2x squared, right? Okay. So forget the shape of the circuit for now, please. I just
I think we should remove that line.
which one?
Yes.
In front of church store. And just make it 2000. Yeah.
Okay. Let's just say
But the line is still going into another.
Another line ahead.
okay.
So, going straight.
Yeah, so calm down. That one shouldn't be an issue. Okay, so what next? We represented this, right? Okay. So next is 2x. Is it? It's different, right?
Yeah, so you have to do it separately.
So this should be which gate?
Asterisk.
That takes in
2 and then
X.
2 and x gives out 2x, right?
We can still use that same thing.
Yeah, we can still actually use the same thing. You get, but let's just separate it for now. Okay, so
Addition.
which gate will this be?
Addition.
An addition gate, right? And then the output, it should be 2x squared plus 2x, right? Another addition should take 1. Okay, so this will be our output, right? Which is 2x squared plus 2x plus 1, right? Do we all agree?
Yes.
Okay, so if, okay, let's now do something, right? This 2 and this 2, let's unify them, right? Because they are kind of like inputs, right? How about x? This x, and x, right? So we can unify them, right? So how we do it? Right. In order not to make it complicated, let's just. Well, we get the idea, right? So, if we want to pass in an input of, like, want to evaluate this polynomial at x equal to 2, what do? We replace this guy by 2, right? Replace this guy by 2. I will just keep like evaluating. So 2 square will be 4, right? Well, let me still keep x and x square. So x square will be 4, right? And so this 2x square, this 4 times 2 now will be 2x squared should be equal to 8. Right. And what next? On this side, we're still going to do like x equal to 2 here. Right. And here will be 4. Right. So what will this guy be? 8 plus 2, right? Which is 12. Sorry, 8 plus 4. And what will be the output? 12 plus 1, which is 13. Right. So after evaluating this circuit, we arrived at an answer of 13. Do we all agree? So we had a circuit, right, that takes in inputs. That input can be variable, right? But then when we wanted to evaluate the circuit, we now passed in concrete values for x that we now use to evaluate the circuit, right? Basically, just using that value for our input and evaluating up to the top. Does that make sense? Okay. So, this makes sense, right? Okay. So now let's basically this circuit is not really structured, right? Structured in a sense that there is no. Normally, we would have expected all our inputs to be on one layer, right? Okay.
I wanted to ask, have we started GKR?
I actually started GKR.
Yeah.
It's easy, right? Well, I've actually started
Just complete
GKR.
so fast.
Wait,
Let's
this
continue.
Introduction.
Yeah.
I thought maybe do like introduction to GKR. Like,
Oh.
maybe we get some change.
Okay.
Yeah,
Okay.
what we are like.
What the goal of GKR is
So
and
we know where we are headed.
yeah. No. Okay, we're still going to talk about that, but I need us to like be comfortable with this first. You get. So, like after talking about like the layered circuits, then I will now like talk about GKR. You get.
So this is the layout.
So normally we expect all our inputs to be at one layer, right? Okay. Like currently, okay, let's try to see if we can make this like a layered circuit. Right. We still want to achieve the same thing. This makes sense, right? I know it's too easy. Okay? I know it's too easy. Or let's still just take it like this. Okay? Makes sense. So let's still just take it like this. I know it's too easy, but then still this same equation. Let's try and give like a structure to the circuit. What was that polynomial? 2x squared plus 2x plus 1. 2x squared plus 2x plus 1. And let's give us. Let's see. So we want to have an input layer, right? Let's say this is our input layer. This is where we're going to pass all our inputs. And this is a polynomial, right? F of x. Our input to this polynomial will basically be just x, right? So you can think of it as
Why are you making it layered?
just to enable us to like have some kind of structure that we want to exploit. Okay, so first of all, we'll be looking at like basically what we're going to be implementing is kind of like the layered GKR, you get. But there's still like the unlayered implementation of GKR, you get. But that one is like kind of more complex. It's not straightforward like what it's not straightforward like what we are currently doing. So for now, let's just look at layered circuits. Okay, so we have a gate, right, which takes in x and x, right, and spits out. Oh. How about now? The network is bad. Okay. Are we together? 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 Okay. Shit. Network is bad. Okay, so this should give us x squared, right? Do we agree? This is a multiplication gate. Right. And we can think of this like as the next. So we can think of this as like the next layer. Like after we have the input layer. When the gate processes the input, we go to the next layer. Does that make sense? So this x squared. Okay. So we can as well still take 2, right? So let's just add 2 to, okay. Let's say 2 is just like a constant. 2 is a constant, right? In this next layer, right? So that we can have like another multiplication gate, right? That takes this and this. Right? Is this okay? And then we get an output of 2x.
X square.
Yeah, 2x squared. Right? So okay, so this 2x squared, what to this will be. So this 2x squared basically we want to now add 2x to it, right? It's not. Yeah?
Can't you just use two, like, this one is going to be
Yeah. So like
just like
the structure is not even
just like this, you can just specify inside 2x there. I don't know, x squared.
no, there's something we're trying to achieve. Or let's just use maybe a different example. Right?
Sorry, can we, I was thinking we just finish with this one, so I believe maybe when we get to the end of it, we might get.
No, like this one will still give us like something similar to this. Yeah. So I wanted like something that will give us like a layered circuit. Yeah. So we're going to define a circuit. We're going to define a layered circuit, and then we're going to pass input to it to get an output. Does that make sense? Like, does this one make sense? Like based on what we did, this one, it makes sense, right? Okay. So now let's like define a layered circuit and then feed inputs to it and see what we get as the output. So say we have a multiplication gate, an addition gate, and a multiplication gate, right? Let's just make it 4 gates. This 2 fits into an addition gate. This 2 fits into a multiplication gate. Then this 2 fits into a multiplication gate. Then we have an output. Right? So this is just us defining our circuit. Right? We just defined our circuit. This to the inputs.
So how do we know the circuit? Is it based on the what we want to do that will now arrange our circuit?
No, for now, for now, we're still going to talk about that.
Okay.
Right. Okay, so these are like the inputs to our circuit. Right. And if we want to evaluate this as circuit, we need like to assign values for each of these variables.
So is this generic or this is specific to that problem?
So this is specific to a particular problem.
That's this one.
This circuit now. It's not the same problem that we were trying to solve initially, the 2x squared plus.
Okay, it's not a different one.
Yeah, this is just a
Or it's
different
just like a
one.
case study you brought out. Or
Yes.
Okay, that's what I was asking. Like, how do we know? Because the way you put
Okay, no, it's just like
yeah,
it's just this one was just
random.
random. This one was just random. You get. Okay. So let's say we decide to take as inputs 3, right? A is 3. You get. B is 5. Okay, people should just give us like random values.
7,
Okay, 7,
4,
3, 4, 2, 15, 28. Okay, so we kind of like assign values to each of these guys, right? So what is the output of this gate going to be? That's 15, right?
that asterisk is that times
Yeah, it's times.
and the x is times. Like it's a multiplication.
Which
The
one?
X there's asterisk.
Upright.
Okay, yeah, this times. Yeah, that's. Sorry. Okay, now, right? It's okay now. Okay. So, when we evaluate this gate, we get 15. Right? If we evaluate this other gate, that is 7 plus 3. We get 10. Right? If we evaluate this gate, we get 8. If we evaluate this gate, we get 43. Right? So we had an input layer, right? We passed it into our circuit and we got a new layer, right? So let's say this is input layer. Let's call this, what should we call it? Layer 1. Layer 1, right? But we have not finished. We're now going to take this layer as the input to the next layer of our circuit, right? So what are we going to get here? 25, 3, 4, 4. Right? So after evaluating, we got a new layer. Let's call this layer 2. Right? And then when we evaluate this, we're still going to get another layer, right? Let's call this the output layer, right? So that'll be 344 times 25. 8. 8,600. Right. So we can see like this computation, we took it as it kind of like generated a layered. We kind of generated a layered circuit, right? And then evaluated that layered circuit to get the output. So if we pass in, say, this input and the output was maybe 8,700, is that a correct evaluation of this circuit?
No.
That's not a correct evaluation of this circuit, right? Okay, good. So this makes sense, right?
So sorry, I might be from running, but yeah, looking at the way you presented this, I'm trying to picture the implementation. So that means we are basically getting our values in an array, and for every step we are getting back an array that moves to the next step until we get our final value.
Yeah.
So we can basically, based on the value, we can basically like, don't worry.
Okay, but does this make sense? So we have an arithmetic circuit. I will want to evaluate that circuit at certain points, right, to get an output. It makes sense, right?
Yeah.
So how about if this circuit had 1,000,000 gates? If this circuit had 1,000,000 gates, it will be slow, right? Would there be any other challenge?
So the million gate are in the symbol, right?
Yes, like let's say only the input layer now itself has like 1,000,000 gates. You get?
It's gonna be expensive.
It's going to be expensive, right? Any other challenge? Like one of the values are 0. Yeah, like is it in the after evaluating a gate? Okay, one of the inputs. Yeah, it can still be 0. It depends on what you want to evaluate the circuit at. Will it be faster? You're still doing multiplication, right? Yeah. It will still go through the process. You're still going to do multiplication. You're still going to do addition.
If 1 million gates, it's going to take a lot of time.
Yeah. So it's going to take a lot of time, right? It's going to be slow. Our computer memory may not even be able to handle it, right?
Yeah, might look like an infinite loop.
Yeah. So maybe not infinite. Let's say 1 million is still a small number to the computer,
Yeah, but
right?
you know, in ZK you can't really, you might have a large field of numbers. So, and at what point does the computer? So, okay, there have been a case where in raw code, the loop is not actually infinite. It's a finite loop. But because it took a longer time to process that loop, it's going to crash.
Okay.
Yes.
Maybe Stack Overflow sorting.
Not Stack Overflow.
Like you're talking about maybe a test now, right? That is how your test will take so long and like the computer will,
Only time I'm like GitHub now. Like,
okay, or maybe
you're trying to
time
upload
out.
something, or you're trying to make a pull request, and it's taking too long.
Okay.
It's not really a test per se. I think someone posted that problem on Starknet Cairo. So there was this implementation it was trying to do. I've forgotten the name they called it. It was something mathematically related, where it's trying to perform a particular computation, but because the field is very large, so it breaks. It throws an error at the end of the day that I think something out of class or something.
Okay.
So yeah, or I know a number of runs think, yeah, that's the error. But it's not a finite, it's not an infinite field, like it's not an infinite field, yeah. So I think there's a way this thing will be large. It will just
throw something, an error like that, right? Okay, yeah. So it's possible. Okay, so the idea now is like we want. I'm a verifier, right? I have a circuit like this with 1,000,000 gates, right? I want to evaluate that circuit, but I don't have the compute, right? So I want to delegate that work to somebody. How can I be sure that if I delegate that work to you, you're going to give me the right output?
some check.
Okay, you're close. But how? Some check how? This is circuit.
Basically
Come on.
start from the output.
Okay, you start from the output.
And then just like the way we did some check for replication where I generate random sample challenges to give me the next layer. So you basically work your way up from output to input. But I think the circuit should be succinct enough to maybe like that if you're evaluating at one layer you can just assume that like since it kind of describes since circuit you kind of like made a description of its input if you are evaluating at one point maybe the output and you get the correct answer you are sure that
Okay. Tragical lemma. But we don't have a polynomial. How are we going to do tragical lemma?
Maybe we can.
But wait, do we understand the question?
What is going
No, I just want to repeat the question so like we can get everybody's input, right? So that was a good attempt. You're also making a good attempt, but let me just repeat the question.
It's going on. It's something now so that we can be hearing it.
Okay, so we have a big circuit, right? With up to 1,000,000 gates, but we don't want to evaluate that circuit, right? We want to delegate the work of evaluating that circuit to another person, for the person to evaluate the circuit and give us a response. But that person can lie, right? Instead of the person to tell us 8,600, the person can tell us 8,700. How can we verify that the person actually ran the circuit correctly and got 8,600? So if the person gave us 8,600, how can we be sure that that 8,600 is actually the evaluation of the circuit on this input layer without us actually evaluating the circuit? We don't want to evaluate the circuit, right? Because it's a very big circuit. But we want to be sure that somebody evaluated the circuit correctly without us evaluating the circuit. Okay, sorry, after I carry.
Do we?
Oh, wait, sorry, Roima, you were saying something. Oh, are you done?
Yeah, there's a way we can represent the operations of the gate. If there's a way we can represent the operation of each gate in a polynomial, then maybe we can use Shiwaziku lemma to confirm that the input is actually equal to the output.
Are you hearing that, sir?
Now I'm going to repeat what she said. So she said, if there is a way to convert the equation of each gate,
Like the operation of each
okay, the operation of each gate
yeah.
to a polynomial. If there's a way to convert the operation of each gate to a polynomial, then we can use Strasbourg lemma to verify. Right, that was what you
But
said.
I'm not going to be going back before I did that because we got this from like a polynomial.
No, we didn't get this from a polynomial.
But then like what we did before this, right?
Huh?
What we did
No,
before
that one was like an example.
this,
Just an example. You get this one is like a completely different example.
So these values are not representing a polynomial, they are just values.
that I want to evaluate the circuit at these inputs. You get, they are just inputs to the circuit. Interesting. That may be a way to think about it. It's asking if they are the evaluation. It said if they are the evaluations of. Okay, if they are the evaluation form of a polynomial. Okay, so I think that is a good way to think about it. Yeah, it's an input to the circuit. What are we trying to do? We don't want to evaluate this circuit. Evaluating the circuit means like doing the operation for each gate. Right?
So, since everything we do basically in GKR has to do with polynomials, this is a problem. I think this is a point where arithmetization comes in. So we can convert the problem to a polynomial, and then from there we can solve it down. I don't know if that.
I get you, but like for now, so we can even think of it was the arithmetization process that gave us this circuit. You can think of it that way. Like the arithmetization process gave us this circuit. Okay, let me not say the arithmetization process, the compilation process. Let's say we had a high-level program, right? How many of us have seen Second before? Second. You've seen Second. Second programming, like, okay. So let's say we wrote our program as a second program, right? And then we compiled it and we got this circuit, right? Okay. So we got the circuit without the values, right? Because it's only when we want to evaluate that it's only when we want to, should I use evaluate now? Or to execute the circuit. Only when we want to execute the circuit, that's why we're going to pass in concrete values for the input, right? Initially, it's just going to be like A, B, C, D, E, F, right? Then I can decide to evaluate it at this point, or I can decide to use this point to execute the circuit. I can decide to use maybe 3, 2, 7, 9. I can decide to use anything, right? Still execute the circuit. You get? So does that make sense?
Yeah.
And the question too makes sense, right? Okay. So Ekarika, you wanted to say something?
Yeah, I want to say like first I wanted to ask, does the verifier know the input?
So you can think of it as like the verifier is giving the prover the input to evaluate the circuit.
So I think you could just pick random input and divide the final output by them and see if either collectively or singularly, and see if they give a remainder of 0. If there's a remainder of 0, I don't know, I'm just thinking like go of the addition part though. I don't know, because the addition part is making it look like it might not result in that. But then if it's something like that, maybe they give a kind of remainder that you would be expecting, it might make the verification faster.
Well, we can't just divide, right? There are different layers. Like, are we dividing the output layer by the input layer, or?
That the addition already makes it.
Does the verifier know how this is going to be executed? Because if the verifier is giving the values, the input, does the verifier know where multiplication will be used and where addition will be used?
Yes, the verifier knows the circuit.
And the output. And he knows the circuit.
But he doesn't know the output.
Okay, so
it's only the verifier knows the circuit, the structure of the circuit, right? There is addition gates, multiplication gates on each layer, right?
Okay, so if
but the verifier does not want to, like, execute the circuit because it's an expensive operation.
So the verifier so the verifier, if the verifier knows the values and the circuit, then basically the verifier can do something like
So which of the values now are you talking about?
the value the verifier is giving.
That is the input, the
input
values
value.
of the
So the
input.
verifier can do like grouping, like values and the operation. I think from there the verifier will be able to verify maybe somehow, I don't know how it was computed or something, but values and the operation that was used or something like that. So based on the circuit, if you present the values to the circuit, you can see the pattern of how it goes, like this goes to something like that.
Interesting.
I feel the circuit definitely has like a property that like enables us see this pattern he's talking about to maybe like evaluating at one point.
People should be coming up with the properties. That property I want to
I
hear.
don't
Like
know.
they're coming up with the
It
property.
has something about like succinctness. Like it just kind of briefly describes what the circuit should be. I don't know what it is.
I don't
Okay.
know what each, let's say represent each layer. Like let's say this that middle layer was a polynomial. Alright, let's say
Okay.
it's one. Then the next layer will be lesser polynomial.
So wait, you said the input layer should be a polynomial, right?
Yeah, let's assume it's a polynomial.
Say a polynomial in,
Evaluation.
like Biliki said,
Yes.
evaluation form,
Yeah.
right? So this will be the evaluation of the polynomial at this is 1, 2, 3, 4, 5, 6, 7, 8.
Yeah,
Right. So if we evaluate, is it a which type of polynomial are we looking at now? Multilinear. So that's 8. 3 variables, right? So this will be the evaluation of the polynomial at what? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right? Oh, sorry. Can you say it now? Okay, so we have the polynomial, or we represent the input layer as a polynomial. Okay, good. So what next?
So I'm thinking, I don't know what I'm thinking is each layer should be a polynomial.
Okay, each layer should be a polynomial. So this one is going to be like this 4, right? That's 2. This 0, 0. This 0, 1, right? This 1, 0. This 1, 1. This 0. This 1. And this is 0. Right?
Which one?
The
Zero one.
sorry.
Okay.
Okay, so for the output, we are going to get a polynomial that if we evaluate as 0, we are going to get the expected output,
Yeah.
right? For layer 2, we are going to get a polynomial that if we evaluate as 0, we are going to get 25. If we evaluate at 1, we are going to get 3, 4, 4. And same thing for layer 1, same thing for the input layer, right?
Yeah.
Do we all agree?
Yes.
Okay, so good. So now that we've had, like, we've been able to represent the result of each layer as a polynomial, right? How about the operations? Right. How about the operations? Is there any way we can represent it?
This times can be like
Okay, let's think of it this way, right? Is there any way we can represent a gate as a polynomial? Is there any way we can represent a gate as a polynomial?
Yeah. The truth table.
The truth table.
Yeah.
Yes.
Okay, how?
That's no arithmetical.
When you do truth table,
That's not arithmetical.
when it's zero, output.
Okay, give us now.
Let's say all.
Eh?
Let's say all truth table.
Okay, like just or.
Like
Then maybe
what
we'll
you
relate
see,
it back
then we'll
to
relate it as a polynomial. So let's draw the truth table.
okay
Then-
for or.
Yes.
Okay.
So 0, 0, 0, 0, 0, 0,
1, 1, 0, 1, 1, 1.
Yeah, so I guess those are our evaluation points now. Those ones, that output.
This one.
The output will be our evaluation points
Okay.
for that polynomial. So that's our polynomial.
So O is for plus and is for multiplication.
Do you really
I not say anything.
Eh? 1 plus 1 is not 1, but for this thing,
No, like this or.
for O it's going to be, yeah, going to be 1. So we use, where we see for the multiplication we use and for the addition we use O.
Okay, I get like everybody's trying to like come up with different ideas, right?
Can we
Can-
try the and for the values on 3 and 5? Let's see what it's going to give us. Then check it if it's the same. If the binary it will give us is the same with the decimal of 15.
You want to carry us
Well,
to
normal and is
you want to carry us
like
to
a 3
linear.
is fine. So 3 is like
Okay. Okay, let's try it. Right? 3 is
0, 0.
right, and 5 is what?
No, I'm talking about the representation of this guy. So, well, let's try this one first.
Okay.
Yeah.
So or right. So we're expecting that if we do this, we are going to get 15. Is that the idea?
And
started like 1 or something?
No.
We're going to get just one now. And this is just 0, 0, 1.
Actually, so it turns the up to. Also, you can even think like if one of the inputs was 500,000, are we going to convert it to binary? All right. Okay, so
What can that one not work?
no, it can. You get, but like there's a way to go about it.
How can you
There's a different like that's kind of like. Because I think that's somehow Binios, somehow. Okay, but okay, see the thing here, right? We want to represent a gate as a polynomial, right? So we want a polynomial. So what is that polynomial going to look like first? Okay. Should we give the output labels? Okay. F of A, comma B
is equal to AB.
is equal to
Is A dot B.
okay. See, we can just think of it as like we already have these evaluations of the polynomial, right? Normally, we want a situation where a polynomial, like if we evaluate at A, comma B, it should give us C. Let's say the output is C. Right. Okay. But let's think of it this way. These are inputs to the polynomial, right? And we've given them labels of 0, 0, 0, 0, 0, 1, 0, 1, 0, blah, 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 right? And this is the output, right? So, we want a polynomial that, wait, this H, this, let's say I, J, K, L, M, N, O. I just labeled. So we want a polynomial that, if we pass in I, right? I is the output of this gate. Like we want to convert this gate to a polynomial, right? When we pass in I, A, B, right? What should we get? We should get 15. Like, want a polynomial that we're trying to, let's say we index this gate. Like, how can, okay, we've talked about how to, say, get the values of the evaluations, right? So how about if we want to get a particular gate, like if we want to talk about a particular gate in this layer, right? We can still think of it as like this gate to be 0, 0 because there are 4 gates here, right? So this gate to be 0, 0, this gate to be 0, 1, this gate to be 1, 0, this gate to be 1, 1.
So what we are looking at here, f into I A B is equals to 15. That means I will be our y. Like, let's look, if we are going back to I will be like our y, and AB will be like
Y1 and X1 and X2.
X1 and X2. Yes, now.
See, we've evaluated the circuit already, right?
Yes.
We've gotten like this other polynomials for each layer, right? We started with this input. We evaluated, we got this, right? We evaluated, we got this, and we evaluated, we got this. So we have like concrete values that we expect each layer to output, which are like right. So we can think of it this way. Say we want a polynomial that's okay. Let's just say we have a polynomial f, right? If we want to get the output of this gate, right? That's basically the index is like 0, 0, right? And this is what is feeding into it, right? That's 0, 0, 0, right? And 0, 0, 1. Right? What are we going to get? So it should give us the expected output. I don't know if that makes sense.
So don't think that this is not necessarily preliminary representation. Not necessarily
Explain again.
Eh?
So this means that this is not necessarily preliminary representation.
No, it's still a polynomial representation. Which one? This?
This means our output is in fact, the way of putting it, our output is also inside the input definition.
almost seen anything right like
If
Okay,
so,
wait.
it
Okay, so let's just call them polynomials first, right? This is f of, let's say f of the input, right? That is this polynomial, right? This is f of layer 1. This is f of layer 2. Right? So this is a layer 1 polynomial, this is a layer 2 polynomial, this is the input polynomial. Right? Like all of us were okay up to this point, right? And this is the output polynomial. So what is the relationship between this input and the next layer? So if we can think of this as a polynomial, right, f of the input, we want a situation where if we evaluate this f of I at 0, 0, 0, what are we going to get? We are going to get 3, right? If we evaluate f of I at 0, 0, 1, what are we going to get? 5, right? We agree?
I.
No, it's the input.
But then there's I there also at the top.
Okay, let me remember. Or let's say f of input. That would be okay, right? Network is bad. Like this is what we want, right? So if we evaluate f at the input, we are going to get like the input layer polynomial. If we evaluate it at 0, 0, 0, we are going to get 3, right? If we evaluate it at 0, 0, 1, we are going to get 5.
If we evaluate at 0, 0, 0 and we get 3, that means the polynomial will have a constant that is 3. Because anything you evaluate at 0, 0, 0 is supposed to give you 0.
Yeah, like anything the polynomial wants to be, well, just it's a polynomial.
Yeah.
This input layer is a polynomial.
Okay.
You get. So anything like the polynomial wants to be. The thing is that if we evaluate it at 0, 0, 0, we get 3. If we evaluate it at 0, 0, 1, we get 5. If we evaluate it at 0, 1, 0, we get 7. Right? If we evaluate it at 0, 1, 1, we get 3. And just like that. You get. So we have, and then this one is also another polynomial, like f of layer 1, right? Right. If we evaluate f of layer 1 at 0, 0, what should we have? 15. Right? Do we see any relationship between layer 0 and layer 1? Let's say relationship. Like, do we see any relationship between layer 0 and layer 1?
It's changing the C.
F of
No.
F of layer 1. F of layer 1 of the first.
For this first gate.
Yes. So if you put the result of the F inputs, like the function of input, like you pick the first two, you are going to get the result of F of layer 1. So let's say F of layer 1 into brackets, F inputs, F inputs.
at 000.
Yeah.
What is that times, right?
Yeah. But it doesn't have to be multiplication, right?
No, we're talking based on this.
Just
We're talking about like this gates now, right?
okay, just that game.
Yeah. Does it make sense?
Wait, what are we trying to achieve? We are trying to, we are still trying to find out how the verifier will verify that. That was where we started our problem.
The problem was the verifier wants to evaluate a circuit, right? But the verifier does not have the resources. So the verifier sends that circuit to a prover to evaluate the circuit and give it an answer, right? So how can it be sure that the prover actually evaluated the circuit correctly based on the results? That is the problem.
So all this stuff we are doing now is a way for the verifier to be sure.
All this stuff was still trying to represent the problem as a polynomial.
In some sense, at every round, the prover gives the verifier a break. So I guess at every round, at every layer, there'll be some polynomials that will be given out to confirm the correctness of the process of the computation.
I think like because all of us have heard some check depends on GKR depends on some check. We have blocked our head to like we're not like yeah, it's as if we're not restricting ourselves to that statement, right? Good and fine, right? Good and fine, like some check depends on GKR, but we first need to represent the problem as like a polynomial, right? So on which we will now perform some check.
So we should forget about some check for now.
Forget about some check for now. For now, we're just trying to represent like the polynomial, or we're trying to represent this problem as a polynomial. And for now, we're just trying to focus on one layer, right? Both the input and the output. Let's focus on that and solve that problem. You get?
Maybe I'm saying if the input layer, can we see it like a sequence?
The input layer.
Yeah, like the first term of the sequence and the second term, I cannot perform an operation on it. It will give me this one. That does not mean that the third and fourth layer I will perform the same operation depending on what I have to get the layer one. So in that way we can solve the problem.
Okay. So, like basically what you're saying is that like each layer will depend on the operation, right? That's true. Each layer depends on the operation. Do we all agree?
Yeah.
We all agree that each layer depends on the operation, right? Okay, good and fine. But does this make sense first?
Wait. Sorry. There are many parts of layer one. Layer one is not just the first.
Okay. Maybe. Okay. Yeah, you can ask.
The way this thing is going now is like we are now going back to that arithmetic constraints. I thought they were looking for arithmetic constraints, so these are my
like the arithmetic.
Like what we did at first, we converted a polynomial to an arithmetic constraint, then converted it to the circuit. Well, now are we taking back
Okay,
the circuit?
okay, no. Like that polynomial was just like the problem statement. So just an example. You get that we just like I was just trying to use that like to make us understand how how like a boolean or an arithmetic circuit flows. You get.
So does it mean that we are trying to convert this circuit back into a system of constraints, like equations constraints? Like,
Yeah, something like that. Yeah, you can think of it. So like based on this evaluation, like one layer depends on another layer, right? Because the input to the layer and the operation will determine the output, right? Like these inputs and this operation will determine the values of this one. It makes sense, right? So like that one was just an example I just used to enable us to understand how like data flows through a circuit per se. So where we want to execute the circuit in a set of inputs.
so all things in equal, we are going back to A times E equals A times E to give us the next one, C times D, C plus D,
Yeah, we can.
like that. Like F of C,
Yeah, C
C plus D equals
plus D. Yeah, should now give us this one,
we now merge them,
right?
equations for the one.
Yeah. So F of E, right, times F of F will now give us like this one. I don't know if it's making sense.
It's not making sense.
Okay. Okay, so like we understand or everybody agrees with the fact that we can represent all these evaluations as a polynomial, right? All of us agree with that fact, right? But now there is a relationship between these values, right, and these values. Do we agree? Like all these values here, there's a relationship between them and these values. And that relationship is dependent on the operation, right? Because based on the operation, if we take two values from here and work on the operation, we are going to get an output here. So there is that dependence, right? If we take two values, work on the operation, we are going to get another value here.
Is this looking like a partial evaluation?
No, for now, just
Because
no. We're still trying to get, say, a polynomial to work with.
yeah, the reason why I said that is because I've learned to look for patterns.
No, I guess.
Now, if you look at this stuff, you see that the first guy is 8, the second guy is 4, the third guy is 2, and the last guy is 1, which means it's breaking into half at every step.
Okay. So, but that is because of our circuit is a fanning. So yeah, it's a binary tree, right? So it's possible that our circuit will not be a binary tree, right? Should we clean this and start again?
Yeah.
No.
Eh?
So sorry.
No, no.
Like the other sense of this is like we are trying to just prove that without evaluating, like without doing this all over again, that this evaluation was not correct.
Yes.
So
So the way okay, I've not finished the like GKR definition, right? So we understand the GKR problem statement, right?
No.
We don't. The GKR problem statement is that the verifier wants to confirm that the execution of the circuit over a set of inputs is the output the prover said.
Yeah.
Right.
That's
Sorry,
the problem
the
statement for
again,
GKR.
please.
Yes.
The present statement again.
Yes.
I want to write it down.
So the verifier wants to, like, this is not textbook definition. No? That's why you're right. Okay. So the verifier wants to verify that the evaluation of the circuit that the prover gave to him is correct, right? Without necessarily evaluating the circuit again by himself. Does that make sense? So, actually, the way GKR does it is by reducing the claim of one layer to the claim of another layer. We can see, okay, the claim on one layer to the claim on another layer. Yeah. So basically, the prover claims that one layer is so and so, but that layer is dependent on another layer, right? So the prover needs to prove that. So I say that dependence. So you're proving that the claim on one layer is equivalent to the claim on another layer. It's still sounding abstract, right?
Wait, are you saying like the claim on the output layer is going to the claim on the down to?
Yeah. So the claim on the output layer is dependent on a claim on this layer, right? Which is dependent on a claim, like the claim of this layer is dependent on a claim on this layer. The claim on this layer is dependent on a claim on the input layer. Does it make sense?
Yeah, that makes sense.
That makes sense. There's a reliance, right? There's a dependence.
The reason why it makes sense is because you told us not to think about some check, but the reason why it makes sense is because everything is still boiling down to how some check works.
Actually, like everything would still boil down to how some check works. But I want us to just like open our minds first. You get? Like it's as if everybody's head is pointing some check, some check, some check, some check. Like how does some check come in? Right?
I'm not thinking of how some check come in anymore, but the pattern, like the dependence is still
Okay,
similar to
yeah,
some
like
check dependence.
like you'll be seeing some kind of similarities.
And
You're trying
that-
to see how you can take advantage
take
of that,
advantage of what you know.
of that stuff. Like it. Okay, so basically, right, we can okay we've gotten a way of representing, like in this tree, if we want to get 8600, we have a way of getting it, right? Just evaluate the polynomial at the output at 0, right?
So if you want to get 8600,
Yes, this 8600.
okay. Yeah.
We just evaluate this polynomial at 0, right? If we want to get 15, we just evaluate this polynomial at 0, 0, right? If we want to get 5, we evaluate this polynomial at 0, 0, 1, right? How about if we want to get an addition gate? Is there any way we can say encode the gates, or say like get a polynomial that if we evaluate it at something, we are going to get the gates at that thing? Like if it's an addition gate, right? What, say we generate a polynomial, and
The polynomial, is it going to consist of all the 4 gates?
yeah, it's going to consist of all the 4
When
gates.
you need to evaluate a particular value that maps to just 1.
Yes, that maps to 1. So if we evaluate at 0, 0, we are going to get a multiplication gate. If we evaluate at 0, 1, we are going to get an addition gate. If we evaluate at 1, 0, we are going to get a multiplication gate. And if we evaluate at 1, 1, we are going to get an addition gate.
So Francis, are we doing it from down to top or from top to
So we are going upward. But for now, like, we're just focusing on
down?
on this one. So once we understand like how it works here, we can use it for any other one, right?
So before we look for that polynomial, so what is the relationship between why do we make use of 0, 0, 0, 1, 1, 0, 1, 1 in that other polynomial, and at the bottom we made use of 0, 0, 0, 0, 0, 1, 1, 0, 1. Like here we are making use of
3 variables. Here we are making use of 2.
representation.
Actually, it's because of the length of the evaluations.
The length of the evaluation.
Like, we started with 8 values, right? To represent 8 values, we need 3 variables.
Okay.
You get? So after evaluating, we got the next layer. It's 4 values, right? And to represent 4 values, we need 2 variables, right?
Okay. Alright.
Okay, you're saying that we can as well use like 0, 0, 0.
No, I'm not. I'm
Okay,
I'm
just
looking for the relationship because
like I get you.
you know.
Like it's as if like it's not matching.
No, it's matching, but it's matching actually. I'm getting it, but you already said that that relationship is not like, you know, this is 8, this is 4, this is, you know, that hierarchy.
That is a song check.
Yeah, no, let's not pause on.
Sorry. Yeah.
Yeah. So I understand it.
Okay. Well, do we get?
Sorry, what if in every layer we now have 3 nodes?
Yeah.
How are we going to determine
The length. We'll pad it to make it 4. You get? But that one is basically like there's nothing there. There's no gate there. Huh? Yeah, we can pad it with 0. So, but did we get the question I asked about this?
Yeah. As a polynomial that when you evaluate it at 0, 0, you get a multiplication as the
Yeah.
when you evaluate at 0, 1, you get addition. When you evaluate at 1, 0, you get multiplication. When you evaluate at 1, 1, you get addition.
Are we getting the operation or we are getting the product of the operation?
We are getting the operation.
The operation is
That would be difficult, right? Actually. So how about for each operation, right? How about if we can have a polynomial for each operation?
Different polynomials all related.
Yes, different polynomials unrelated for each operation. How would that help us to encode the operations for this layer?
So you can have like a add polynomial
Yes,
and multiplication polynomial.
and a multiplication polynomial.
Mhm.
Yeah. So what is the add polynomial going to look like?
Okay. So it's going to evaluate to something like maybe 0 if
You're on track.
let's do truth table for it.
Let's do a truth table for it. Okay. So is there any need for a truth table?
okay, to evaluate to
Let's just f of it's two variables, right?
Yeah.
This 0 0, right? 0 1 1 0 1 1.
yeah.
Right. So that's f of a b. What is it meant to equal? Okay, first of all, like we said, two polynomials,
Mhm.
right? We have an add poly, and we have a mod poly,
Yeah.
right? So if we evaluate, okay, let's say this add poly now.
I see.
Since there are two variables, right?
Mhm.
As 0 0, as 0 1, right?
Yeah.
1 0, at 1 1, right?
Mhm.
Also, this mod poly, we are going to evaluate as 0 0 2, right?
Yeah. At 0 1.
Mm-hmm.
At 1 0. At 1 1.
So what are we expecting?
So I think for add, I'll give you one when you actually like maybe combine 0 1 1 0 together. I think it will evaluate to 1 for add.
Huh?
I think I will give you 1 on the instance of 0 1 1 0. Or
Okay. Oh, actually, like, this add poly, right? You know, we are dealing with
this second.
a gate, right?
Yeah.
And a gate has outputs and inputs. So would this be a good way to represent it?
It will have you. I think you need to represent it with outputs and then input. So it will be like maybe a tuple of 3 elements. I
Okay.
don't know.
So outputs and inputs.
Yeah.
Okay, so just tell me what.
Output to be one value, maybe 0 or 1,
Okay.
right? And then
Okay, let's focus on this. On
what?
on this one, right?
On what?
This one.
0 1
That layer 1.
Yes.
Okay. So I'm seeing 0 0 to be for add. I'm
Yeah.
seeing Okay, yeah. So it's going to be 0 1. Like the output will be 0 1. Are we using the binary equivalence now, not just the output? Are we?
Huh?
Like we're using the binary equivalence, sort of, not
Yeah.
the outputs values themselves.
Yeah, the
right?
binary equivalent, right? Because we're working with
Okay.
multi-linear,
Okay.
right? Okay.
So I'm saying 0 1.
0, 1.
Yeah. Is it?
Sorry,
Yes.
0, 1.
Yes.
Uh-huh.
Then you have a tuple of 0 0 1 0 and 0 1 1.
And what is it meant to give us?
I think it will be 1.
It should give us 1.
Yes.
Can you explain why? You're right,
Because,
but explain why.
because if you look at the circuit, right,
Yes.
the
Which is
the circuit from layer 0 to layer 1.
this
exactly
one,
that
right? Okay.
Like the output, the only place we can see basically the output for the add gate is when 0 1 0 and 0 1 1 comes together.
So this 10,
No, it's
should I remove it so that it doesn't confuse us? It's actually 0, 1.
Yes.
The 10 is the
It's the
result,
value.
the value. It's not going to confuse us, right? Should I just leave it there? Okay, so you say the output is 0, 1, right?
Yes.
And the input is
0 1 0.
0, 1, 0, which is 0, 1, 0,
Yes.
and 0, 1, 1.
Yes.
So it should give us a 1.
Yes. Because
Meaning-
that's like it's basically on in that layer.
Yeah, because there's an add gate there, right? Is there any other place that we should expect a 1?
Yes. At
Where?
1 1.
At 1, 1.
Yes. You have 1 1 0
1, 1,
0. Like the next
okay,
value is
1, 1, 0,
and 1 1 1.
and 1, 1, 1.
Yeah, the output for that is 1.
The output will be 1.
Then every other thing is 0. So you can have maybe an output of, let's say 0 0.
So the Boolean hypercube, wait, sorry. Does this make sense?
Yeah, but why does 1 0 0 and 1 0 1 not? Why does 1 0 1 0 0 and 1 0 1 not give 1?
1, 0, 1, 0, 0, 1, 0, 1. This is a multiplication gate.
It has a point where it is on also.
No, it's not. It's not an AND gate. You know we are separating like.
So I just dealing with AND gate.
No,
So-
add.
Yeah, I know that like.
There's an add coordination and there's a multiplication coordination. But we can only see 2 add gates there
Yes.
that gives you like a value in layer 1 from layer 0.
Yeah. Yeah.
So that means the places where multiplications are, they will basically give you 0 values because there are no add gates there.
But multiplication is a combination of addition.
We are looking at it with, forget that multiplication part. You get?
Everybody seems lost. Everybody's actually lost. Yeah. Okay. So we're going to do it again, right? Let's start again. Let's start again. If you're lost, maybe in some check, if you are lost, they say if I go back to the video. Here, if you're lost, you may go back to the video and you'll not still find yourself. You get? So if you're lost at any point, please ask. It doesn't matter how many times you bring the class back. Just ask. Ask questions. Ask questions. Ask questions. Okay. So we were like, we have the circuits, right? We have the circuits. Should I remove all these numbers? Okay. So we have the circuits, right? And we have a set of inputs that we want to execute on the circuit, which is this set, right? And it's a layered circuit. It takes in input, it works on it based on the operation, and it gives an output, right? This output is still the input to another set of gates, and it gives another output, right? And then we feed it into another set of gates to give us another output, right? So looking at this, basically, like, all of us agreed that we can represent the evaluations for each layout as a polynomial, right? Like, after executing the circuit, remember that proving only starts after execution, right? You cannot prove what you have not executed, right? So you need to execute the circuit to actually get your, say, your witness values or your trace values, right? You need to actually do the computation so that you can get a proof that you actually did the computation, right? So doing that computation is evaluating the circuit, right? And we can think of these intermediate values as kind of like evidence that we have actually done these operations on the inputs to get these ones, and then this set as evidence that we performed operations on this one to get it, and so on, right? So based on the fact that we said we can think of this as polynomials, that means if we evaluate the polynomial at, say, for this first one at 0, 0, 0, we are going to get 3, right? If we evaluate it at 1, 1, 1, we're supposed to get 28, right? It makes sense up to that point. Are we sure? For this one, if we evaluate it at 1, 1, we're expected to get what? 43, right? So we can think of this as, or as of these polynomials as the, can I say, the polynomial that encodes the evaluation for each layer, right? This is the input layer, this is the evaluation after we have passed the inputs in. Does that make sense? Are we sure?
Yeah.
What is the point of that? We are saying the values at this point. What are we evaluating? What polynomial?
This is the polynomial. You can think of this as the polynomial. Yes. Is it not? Like, if you think of it as the evaluation forms of a polynomial.
That's for the first.
Yeah, even this, can't you think of it as, it's still an array of values, right? So you can still think of it as a polynomial or the evaluations of a polynomial, right? Since we are working in evaluation form, that polynomial, the coefficient form or representation of that polynomial doesn't matter to us right now, right? Because whether it's the coefficient form or the evaluation form, they are still talking about the same polynomial, right? So each of this is a polynomial, right?
If in a situation whereby the inputs are not like they are not
A power of 2.
are you going to extend it?
Yeah, you can pad it with zeros.
Or you can do like that?
You need it to be like, if you're talking about like a binary, like your circuit, if your circuit is kind of like a binary representation, you will need to pad it, right? If not, you will not be able to like collapse it up. That makes sense.
I think we can okay, it has to be binary.
For now, you can think of it that way. It's not always going to be binary. Like in real life, like applications. But what people will be implementing, you will make it like binary. Or anyhow you want to implement it, you can decide to make it not binary. But there's every one of us understand up to that point. Like we can think of all this as evaluations of a polynomial. Huh? So also we need a way to represent each of the gates, right? Because it's actually the gate that is doing the work, right? And the output is dependent on the gate, not even the input. If the gate is an addition gate, right? If the gate is an addition gate, the output will be different. If it's a multiplication gate, the output will be different, right? So there has to be a way for us to encode the operation. Do we agree? There has to be a way for us to encode the operation, right? And how can we do that? How can we encode the operation? Normally, when we want to encode data, we basically represent that data as a polynomial, right? That's basically what we did for these guys, right? So now we need a way to encode the operation, the gate. We need a way to encode it as, like we need a way to encode it. And since we are working with polynomials, we need a way to encode it as a polynomial.
The gates.
Yes, the gates. Sorry.
So I think from your explanation now, since what we are trying to encode is the gate, that's where which is falling back to his
idea. Yeah.
So that place where he was doing those stuff where the output was coming out to be 1, that's telling that okay, at this point that addition is on here, so that 1 means it's on, while on those other subsequent areas multiplication will be 0 because multiplication is off there. So that means if we move over to the multiplication poly, those we pick the binary representation of those guys. The same thing is the, so for that side the multiplication will give us 1, while for the addition it will give us 0.
Okay. Yeah. But like I need everybody to follow. So I'll go over it again. But you get. Okay, so now we're trying to represent each gate as a polynomial, right? Since there are basically 2 operations here, right? Since there are basically 2 operations, we can decide to have a polynomial for each operation. Like addition will have a polynomial for it, a multiplication will have a polynomial for it. Does that make sense?
Smart.
I have a question. Will this polynomial persist across all
No, it won't persist. It won't persist. This is like particular for this layer. But you get the point. Sorry.
Does that mean that if we move to the second gate now,
This second one, right?
yeah, the second gate, the addition there is different from the first one?
Yes, it's different.
Okay.
It's different. Is it making sense?
Yeah.
Are we sure?
So,
Huh? Sorry, DK. After DK.
okay, so if you want to represent, the way when you answered the question, he was like represented the addition at 10 as a polynomial, the result at 10 as add poly of 0, 1, 0, 1, 0, and 0, 1, 1. So if you want to do the same for 15, would it be add 0, 0, add poly 0, 0, then mod poly 0, 0, 0, 0, 0?
For now, like, let's just, it's not 15. Let's just leave the 15. I get.
Okay.
Yeah.
Okay, so what I'm asking is, even if it's not 15, would you construct?
Sorry. Okay.
Yeah, as you're climbing up the tree, right?
Yeah.
If you're trying to get from the addition
Of which one?
or the
This
multiplication
one.
of
Or this one?
the plus and the second layer,
This layer or this layer?
that one.
This
Yes, that one.
this one.
No, that one.
Network.
Yeah.
Not this
The
one.
one where the arrow is, where the first
Okay.
one is.
This one.
Yes, that one. But you're coming from AB.
No, you'll be coming from this point now. Right?
Okay.
Because these guys have already finished doing their work and we got an output here.
Yes, so if you want to present it at that point, would you do add poly that takes in a mod poly?
No. Okay, I'm coming. Let's just do for this first layer. You get. So we have addition and multiplication, right?
Forgot something. Someone had a question.
Okay, sorry. What was that?
In this particular circuit representation, we only have two operations. So like if there are other operations, we don't have a polynomial.
You have, yes, if there are other operations, you're going to have a polynomial for each of them. You get. Are we together? Velikis, are you with us? Any question? Sir? Sure. A character. Are you with us?
Sure.
Mitch. Goodness. Forgive him. So is everybody with us? Okay, so we said for each operation we are going to define, like for each operation on each layer, right? We are going to define a polynomial, right? And How are we going to define that polynomial? So for the add, the output of any gate on this layer will usually be like two variables, right? Like based on the labeling. You know, when we're labeling for the inputs, this is 0, 0, 0, right? Which is three variables. But when we're labeling for the outputs, this is 0, 0, 0, 1, 1, 0, 1, 1, because of the length of the gates. Does that make sense? So to get the output for at gate 0, 0, right, we have 0, 0, and then it takes in two inputs, right? Or let me just say this is A, B, this is C, D, E, this is F, G, H, right? Let me take this guys off. Okay, I think let me just the evaluations that are there are confusing us.
Your wife now, your wife already understand.
No, we're still going to do it again. We're still going to do it again. So we have a multiplication, we have addition, we have multiplication, and we have addition.
Is it like we always start with multiplication, or we are just doing it for example's sake?
This is just an example. Okay. So first of all, let's label.
Is that according to the last example?
No, it doesn't need just a random. Yeah. So let's index all the gates, right? So that if we want to talk of like a particular gate, we can know how to address it. Like a particular gate at a particular layer, we can know how to address it, right? So there are 4 gates on this layer, right? So how are we going to label it? Huh? 0, 1, 1, 0, 1, 1, right? There are 2 gates on this layer. So how are we going to label 0 and 1? There's just 1 gate on this layer. 0. Right?
1, 0, and 1.
Huh? For which one?
In root.
No, this is just 0.
Why not 1?
Because we have just 1 gate here. You get?
See the gate like an array. Like an array.
Okay. So let's call this layer 1, right? And let's call this layer 2 and layer 3, right? So if we say layer 1 at index 0, 1, which gate are we talking about?
So for instance, we talk this thing, so it's multiplication that was there. But it doesn't mean.
You say it's
Yeah,
not
it doesn't mean.
Anything.
Yeah, it doesn't mean.
They're not the same people.
We can as well, like, I can't remember it if you can.
Okay, anyhow, yeah.
You say multiplication, Abby? Let's do it. So I was saying, if I say like, which operation is at layer 1, index 0, 1, which gate is that? It's an addition gate, right? How about at layer 2, index 1, which gate? It's a multiplication gate, right? Okay. How about at layer 3, index 0?
multiplication.
It's a multiplication gate, right? Good. So, okay, based on the input, let's just say this is 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. This makes sense. Does this make sense?
Yeah.
So if we want to identify a particular gate, right, to be able to identify a particular gate, we can use these labels to identify a particular gate, right? We can say the gate where the output is 0, 0, and the input is 0, 0, 0, and 0, 0, 1. So which gate are we talking about? This multiplication gate.
Multiplication at index 0 in layer 1.
Okay. Yes. So if we say we are looking for a gate at, guys, we are looking for a gate now where the output is 0, 0, right? And then the input is 0, 1, 0 and 0, 1, 1. Which gate are we talking about? Wait. We are looking for a gate where the output is 0, 0. The input is 0, 1, 0 and 0, 1, 1. Which gate is that? It does not exist, right? Do we agree that it does not exist? How about if we are looking for a gate where the output is 1, 0, right? But the input is 0, 1, 0 and 0, 1, 1. It does not exist. Good.
Oh, it now makes sense. It makes sense. So that stuff he did, it's the output where the input is this and this is equal to 1, which means true.
Yes.
It exists. Then in places where also it will be 0, that means it's false.
Exactly. I don't know if we understand. So, if we want to outline how many add gates do we have on layer 1? 2 add gates, right? So, let's say we define an add poly, right? We define an add poly, and I want those 2 gates, those 2 add gates. So people should tell me the labels for those 2 add gates.
0, 1,
0, 1.
0, 1, 0.
0, 1, 0.
No, like give me the complete
0, 1,
0, 1, 0.
0, 1, 0 and what?
0, 1, 1.
0, 1, 1. Right? And this should give us a 1, meaning there is a gate
Yeah.
there. Does this make sense? Are we sure?
Yeah.
Are we sure?
Yeah.
How about the second? 1, 1. 1, 1, 0. 1 1 1, right?
Yeah.
That means there is an yes, there's an add gate. If we sum this polynomial over the Boolean hypercube, what are we going to get? If we sum the add polynomial over the Boolean hypercube, yes, we are going to get 2. Why?
All of that, like evaluations actually.
Good. 1 plus 1 is 2, right? What does 1 plus 1 is 2 mean?
Okay, the evaluation at 0 and the evaluation at 1.
No. It means that there are just 2 addition gates on that layer. Does it make sense? If we sum this add polynomial over the Boolean hypercube, we are going to get 2. This is 1 and this is 1, right? Every other place over the Boolean hypercube is going to equate to 0, right? So if we sum this polynomial over the Boolean hypercube, we are going to get 2, meaning that there are 2 add gates on this layer. Yes. Does it make sense? Are we sure? So basically, any other place we evaluate this add polynomial that is not these 2 places, we are going to get a what? A 0. We agree? How about more?
So, sorry, for the purpose of like revision, can we like finish up the add for the other places that are not visible, or should we just leave it like that and just assume?
Okay, for the other places.
Yes.
Man, this is a polynomial in how many variables? 1, 2, 3, 4, 5, 6, 7, 8.
No, we are not evaluating. No, just okay. Continue.
No, we don't need to evaluate because it will equal to 0, right? But we are going to be counting like 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 1 0 0 0.
That's not what I'm saying. I'm not saying.
Okay, instead we should just outline
What
it.
I'm saying is,
Okay.
you know, we have add for this guy.
Yeah.
Like what you were doing before. You know, on this add part, you created like 4 adds. You understand? So the add on.
Okay.
Equate to
So okay, I get you. Okay, so if we have add at 0 0, 0 1 0, and 0 1 1, what should this equal to? Huh? I will not say anyway confidence.
0 0 0.
0.
Yes.
Yeah, like that gate doesn't exist, right? Because we are meant.
using the gate. They are using the
Which one?
Since this is add, I thought we are doing for all the values and the
We need to be 0 0 0 and 0 0 1.
So it's like layer 1,
yes,
right?
with 0 0 0 and 0 0 1.
Yeah, that is when it will give us a valid.
But we are
Okay.
on add, so
Yeah, we are on add,
yes.
exactly. This is a add polynomial.
Yes.
You get. So even if, like on this add polynomial, even if we evaluate it at 0 0 0 and 0 0 1, we are still going to get a 0, right? There exists a valid gate like that, but it's not an add gate. So we are going to get a 0, right? If we have add at 0 0, 010 011. A gate like this does not exist, so we're still going to get 0. Does it make sense?
Yeah.
Are we sure?
Yeah.
It makes sense up to this point.
Yes.
Now let's do 4. Okay.
So what I was thinking was, like, like you said, before we try to verify, we had already performed the execution, right?
Yeah.
So we already know what we are looking at. So there's no point trying to evaluate at a gate that doesn't exist. Let's just evaluate at a gate that exists, but not on the. So let's just evaluate at the product of the 2 multiplication, and since it's not a multiplication, we get 0. So instead of trying the ones that doesn't exist, it will take us through like a very large loop.
Okay. No, I just put that one so that
Okay, alright.
at least you get. But let's also do the other one. So that will be add at 10 100 101. What is going to give us? 0, right? There is a gate there, but it's not an add gate.
Yeah.
Hope everybody's following. Okay, now let's look at more. Still for layer 1. Right. Okay. So just to ask again, this add polynomial, if we sum it over the Boolean hypercube, what is going to be our answer? 2. What does that mean? There are 2 add gates on that layer. Right? Okay. So, for the more gate, if we evaluate it at 0 0 0 0 0 0 0 1, what should we get? 1. Good. Still on the more. If we evaluate it at 0 1 0 1 0 0 1 1, we are going to get 0, right? For the more, if we evaluate it at 1 0 1 0 0 1 0 1, what are we going to get? 1 0 1 0 0 1 0 1. We are going to get more. 1, right? How about, okay, at 1 1 1, what is it? 1 1 0, right? We are going to get 0. There's a valid gate there, but it's not multiplication. Any other place we evaluate it at, it's going to be 0, right? So if we sum the more polynomial over the Boolean hypercube, yes, it will be 2, right? Meaning there are 2 more gates on that layer. We agree?
Yes.
Okay. So now let's look at layer 2. Layer 2 has how many gates? 2 gates. How many add gates? How many more gates? 1 each, right? So if we are defining for layer 2, So for layer 2, right, if we still have like 2 operations, right? We're basically working with 2 operations. Add or more. So for the add, if we evaluate it at 0, 0, 0, 0, 1, what should we get? 1, right? If we evaluate it at 1, 1, 0, 1, 1, we are going to get 0, right? There's a valid gate, but it's not a more gate, right? If we evaluate it at 0, 1, 0, 1, 1, what are we going to get? It's not a right combination, right? It does not exist. So we're going to get 0. So this makes sense, right? This is a polynomial in how many variables? No. A polynomial in 5 variables, right? Is it not? Because for the output 1, right? For the input left is 2, right? So that's 3 already. And for the input right.
Okay, we are seeing it as a very polynomial.
No, not it's multilinear.
Multilinear is AB. Like 0, 0 is AB, the next one is AB.
Yeah.
So if it's AB, then it's not 5 now. Because the first 0, 0 is AB, where A and B are 0, 0. And the second one is AB, where A is 0 and B is 1.
Yeah. But now we're talking of the add itself.
Okay.
0, 0 is made up of addition of 2 variables. And 0, 1 is addition
of 2 variables. And then the output 0 is 1. So the total variable for the add is 5. So if we want to sum this polynomial over the Boolean hypercube, we are going to be evaluating it at 2 to the 5 number of places, right? And then summing it. Because there are 5 variables, right? So all possible combinations of binary numbers in 5 bits is 2 to the 5. That is basically the sum over the Boolean hypercube of this add polynomial. Okay, let's just forget about it, right? But this makes sense, right?
We didn't necessarily need to do all this other ones though.
Yeah. We don't need to, right? But let's just do 4 more. I know it's like we already understand, Abby. But let's just do 4 more. So we have more at 0, 0, 0, 0, 1. What are we going to get? 0. Is it 0?
No. Yeah, 0.
Okay. So more at 1, 1, 0, 1, 1.
1.
I'm going to get 1, right? More at 0, 1, 0, 1, 1. 0, right? Basically, any other place is going to be 0, right?
So that why are we not computing 1, 0, 0, 0, 1?
Huh?
Why are we not computing 1, 0, 0, 0, 1?
1, 0,
If
0,
we can
0.
compute 0, 1, 0, 1, 1.
that one is just like an odd example, just to tell you that it's not like an odd example that will tell you that anywhere it doesn't match zero.
I was just, I guess.
No, if we want to do everything, if we want to write everything, like we are going to be writing like 2 to the 5.
Yeah, like
Different.
because I was like, if we added that last one, then why did you just add that one? So like if we are doing away with those odd, I think
That means
doing
we
away
can
with
go
those
back
odd,
to the
just-
first one when we have
just go
4 and do all the odd things. We have it like a lot of
That will be a lot of examples which are not necessary, right? Because they all evaluate to 0. So, like, do we understand up to this point?
Yes.
So now we have a way of representing each gate as a polynomial. Do we agree? So now we have a way of representing each gate as a polynomial, true. But we want to represent each layer as a polynomial. Right? Because we know that the relationship is like one layer depends on the layer below it, right? That layer depends on the layer below it up to the input layer. Right? Are we together?
Yes. Yeah.
Sure? So we need a way to represent a layer as a polynomial. And what is our polynomial going to look like? That's what we're trying to figure out now. We now have to represent a gate as a polynomial. But now we need to represent a layer as a polynomial. And what is that polynomial going to look like? Does anybody have an idea? Yep.
so it's scroll up to it. Yeah. Scroll up.
Is this okay?
Yeah. So, when you say we are representing each gate as a polynomial, that means for the add, right? Here, the 0, 0, 0, 0, 1, is that the polynomial?
No, that is for the gate, right?
For the gate, right? Is that the polynomial for that gate?
For, like, the add polynomial
Yes.
is going to be a polynomial, let's say, add A, B, C, D, E, right? Where this is for the right, this is for the left, this is for the output, right? Basically, this is the left, this is the right, and this is the output. Does it make sense?
I think it's the left, the right is at the S2.
Okay. Wait,
That's left.
this left,
Yes. And
and this right.
yeah. So, okay, this is the polynomial.
So this is the polynomial. So this is the polynomial that I was telling you that if we sum over the Boolean hypercube,
To give us 1
yeah, it will give us 1 for this
for this.
layer now, right? Because there's just one additional gate,
Okay.
right? We can see that that polynomial has how many variables? 5, right? Where this 2 is for the left, this 2 is for the right, and this is for the output.
Okay, so this is the polynomial, or we are representing the polynomial in this format or this format, in the Boolean format.
Okay, no. Like, here we're already evaluating the polynomial,
Yes.
but this is the polynomial, right?
Okay, so in a case where there are two add operators, so that means we are going to add the polynomials together to get one polynomial for that particular layer.
No.
Or are they standing independent?
No, the idea is we are summing the polynomial over the Boolean hypercube, right? So at one of those iterations, we are going to hit this first gate.
Okay.
Like if there are two add gates,
Yeah.
at one of those iterations, we are going to hit the first gate, right? And then at another point in the iteration, in that sum over the Boolean hypercube, we are going to hit the second gate.
Okay. Right.
Does that make sense? Are we sure?
Please repeat this sequence.
Like when I said like if we sum this polynomial over the Boolean hypercube, we are going to get 1 for this case, right? But in this other case, for the layer 1, if we sum the add polynomial over the Boolean hypercube, we are going to get 2, right? Why? Because when we were summing over the Boolean hypercube, when we got to this combination 0 1 0 1 0 0 1 1, we got 1, right? Then we kept on summing like other combinations. It was just 0. 0 plus 1 is still 1. When we got to this other iteration at 1 1 1 1 0 1 1 1, we got another 1, right? Then when we added it to our cumulative sum, that's what made it 2, right? So basically summing this polynomial over the Boolean hypercube now gave us 2, right? It makes sense. Okay. I don't know if it answers your question. Okay. So now we've seen a way to represent a gate, right? So we now need to look for a way to represent a layer.
Francis, is it that the only celebration that is used in arithmetic gate is just multiplication?
For now, like that's what they call custom gates, but that's why for now just take it as addition and multiplication. But if you have say another gate, you're going to have like a polynomial also for that gate. You get?
So this add polynomials and non, that's all representing the gates.
Yeah. Just the add and the more.
These are not represented.
No. We are not done yet. We are not done yet. But is everybody like, are we together up to this point? Are we sure?
Yes.
Okay. So the next thing now is that let's construct a polynomial, right? We know how to represent a gate, right? And we also know basically, or we have said, it's us that said though, it's not me. So we have said that we can think of each layer's evaluation as a polynomial too, right? In the one I cleaned. Like, should we do it again so that we'll just have like concrete values? So, what are we going to use here?
We have 3,
Uh-huh.
5, 7, 3, 4, 2, 15,
28.
20.
Oh. Thanks.
Smart.
Samuel.
Are we like, are we together?
Yeah.
Are we sure? If you have any questions, ask before we continue, please. Okay, so while we're filling it out, if you have any questions, just ask. So this next one will be what? People should just give me the value. Don't want to crack my head.
15,
Yeah?
10, 28, 43.
843.
Yes.
What is this one?
25, 34.
At the output, 8600. Right? Okay, now, since we have a way of representing a gate, right? And we said that each of these evaluations are a polynomial, right? Can you people give me a polynomial? I want a polynomial that if I evaluate it at if I evaluate it at 0, 0, 0, 0, 0, 0, 0, 1, I'm going to get 15.
Can you come again?
Like, we understand how to represent a gate as a polynomial, right? And we also said that each of the evaluations, like basically of each layer, can be seen as a polynomial, right? So I'm looking for a polynomial that if I evaluate it at any correct wiring, right, I'm going to get the output for that gate, basically, right? A layer that, or a polynomial that encodes a layer, can basically think of it as that, like a polynomial that encodes a layer. We already have the building blocks, right? So let's construct the polynomial now.
So that means we can represent it with the polynomials of the gates that form that layer.
Yes.
Okay.
But technically, 0, 0, 0, 0, 0, 0, 1 have only one valid output, which is 0, 0 in this example, for instance. So why still pair 0, 0 up with 0, 0, 0, 0, 0, 1 when pairing it
Sorry.
with
I don't get it. Please just come again, sorry.
typically 0, 0, 0, 0, 0, 1
0, 0,
0
0,
0, 0, 1 has one right output in the sense that it has one output, it has one valid output. Meaning that if you try to pair it up with another of the outputs, it's invalid, it's 0. So then, why then include 0, 0 in the input box for getting that same 0, 0, for getting 0, 0, 0, 0, 0, 1? Why not just call it 0, 0, 0, 0, 0, 1 like we normally
Okay, so if I got you right.
Let me use another one.
Wait. If I got you right, you're saying like for add, right? Instead of 0, 0, 0, 0, 0, 0, 0, 1, right?
Yes.
We can do add 0, 0, 0, 0, 0, 1.
Yes, because technically, like 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 0, 1, all will give 0 at the end of the day for mod, whether for mod or for add, because they are technically not on that from that branch. So why add that 0, 0 when it's more like we are just attaching the result of that two addition to of the two computations that yields that particular result in the same tuple array for that same data.
So
Sorry, Francis. I think I get what he's saying. He's saying that why do we have to like write basically the output binary form basically there. That why, since we know that add is only present in like the second and fourth positions basically. And why can't we just write the input that we know, oh, this input basically just combines forms that add. I don't know if you get.
yeah, but it's because of the way we are representing it, right? This input might have been from here, right? There might have been, right? This is just an array, right?
Yeah.
So it's possible that is this 0, 1, 0 that actually fed into like this gate. Does it make sense?
Sure. So meaning that we are kind of like writing the output and the resulting input.
Yeah, because that is what forms a valid gate.
Makes sense.
Yeah.
Sorry, are you saying that, I don't know, are you saying that like the output and the input, like we are passing into the same array?
Yeah, like we are passing.
So you should do it like 0, 0, 0, 0, 0, 1 equals to that.
Yeah, something like because at the end of the day we're still computing it to that same.
So the goal basically is we are trying to get a formula. It's not a formula in this case that works regardless of the structure of the circuit. You're going to get one formula that regardless of the kind of circuit you're doing, it works. So now this way, what you're saying is correct, right? If you know that your circuit is always going to be like this, what you're saying is correct. You always know that it's always like passes into that thing.
Yeah.
So you don't need to have the output. But GKR itself allows a whole range of circuits. So like there's something called CKML, right? Where you can represent a neural network as a GKR circuit. And a neural network, every node gets into every other node.
Like how we go.
So in that case now, it's not just two, for example.
Oh, it can go beyond two.
Exactly. Yeah. So it all depends on the kind of circuits that are. But I think for now, I think we just finding two. But then even at that, it doesn't have to be like what you drew now. That first one could have gotten its input from like the last input.
Yeah.
Or so and two inputs might go into two different outputs. Like that's 00 and 001. Then they're going into that gate. That same 00 and 001 might go into the next gate.
Yeah. No, why I asked the question was because two were always going into one.
Yeah.
Two were always going into one. So I was like, I mean, it's.
I think what we can do tomorrow is once again we'll design the we'll restrict the circuit. So we'll start like a very, very simple circuit. Then we'll design the general formula for that circuit. Then we'll increase the difficulty. We'll get another circuit that adds more. Just like when I start with a circuit that just has addition gates, right? Design the formula for that. Then I'll add multiplication gates. So that you can see how like the design process occurs. Yeah. I don't just
Okay. So, like, are we together up to this point?
Yeah.
Are we sure?
Sure.
Okay. So, as I was saying, like, we're trying to get a polynomial, right? Such that if we evaluate it at certain labels, we are going to get the expected output, right?
Yeah.
So if we evaluate it at say 0, 0, 0, 0, 0, 0, 0, 1, we are going to get 15, right?
Yeah.
If we evaluate it at 0, 1, 0, 1, 0, 0, 1, 1, we are going to get 10. If we evaluate it at 1, 0, 1, 0, 0, 1, 0, 1, we are going to get 8. And if we evaluate it at 1, 1, 1, 1, 0, 1, 1, 1, we are going to get 43. Right?
Yeah.
We need a polynomial that satisfies that, basically. Okay.
Well, doesn't that mean that
Like
the
one
first
to- yeah.
variable is not
Yes,
necessary
one.
for the
One.
But that would mean that the first and the third we have a kind of similarity. Because they are.
The first and the third.
And the third, yeah, like since they are like kind of like they have a multiplication. It's
No, but we've already defined a multiplication polynomial, right? And we've already defined an addition polynomial, right? And we basically said that the evaluations of these circuits are also a polynomial, right? With all this information, we need one polynomial.
Can we sum them? The gates, the polynomial of the gates we got in before. Can we like sum them since like the layer has like 4, 1, 2, 3, 4, and the R's and the null are like 2, 2. So can we just sum them to represent the layer? I don't know if you get what I'm trying to say.
Can you give me an example?
Like you can say that add
Mm-hmm.
add of 0, 0, comma 0, 0, 1, 0, 0, 0, 0, 0, 1.
There's going to be more.
Oh, yeah. So that should be more actually.
Okay.
Plus add of 0, 1, 0.
Out of 0.
So
Out of
one zero.
no, sorry, 1 0. Thank you. Yeah, 0 1 0 0 1 1. 0 1. That should be 0 1. Okay. Small of 1 0. 1 0 0 1 0 plus add of 1 1 1 1 0 1 1. Yes, I don't know if you can represent the players.
But if it's something like this, like referring to, I don't know whether it was Lagrange basis, where like you basically, when you want to evaluate at one point, you basically set down 1 to 1, and then every other thing should be 0 to give you the value for that kind of gate position, but I'm not sure.
It's a good attempt, but it's still far.
Okay.
Small.
First one.
Eh?
I think our first one there. That more plus add.
Okay,
Right?
yeah, this small plus add.
Yeah, you just say is equals to top.
It's equal to
Pull up. What is up?
this one.
Yeah, I think it was 25.
This 15.
Oh yeah, it was to 15 years. Sorry.
So no need for this time.
Yeah. We are still going to divide it for this.
Okay, equal to 15.
Yeah.
But we're missing.
What about 10?
Hmm?
Where is it?
What is 10?
More
Add is 10, then more is 15.
That's 25.
Everything is fine.
But we're still missing something, right?
Sorry, I meant 25. I meant 25, not 15.
This one, 25.
Yeah, I meant 25, not 15.
Like, I thought it should be 15 now. This is input of 3 and output of 1. That is basically this. Right?
Yeah, so that's 15.
Yeah, that's 15.
Yeah, the other side.
This other
is 10.
side,
Is 10.
add.
That's 10.
Okay, so equal to 25.
25.
But everything should be everything should be basically like with
And yeah,
But that one is
yeah,
layer 2 now. That implies layer 2.
yeah, this is for layer 2. This one is for layer 2 basically now.
Wait, but let's remember, like, this is eval 1, right?
Yeah.
Eval input. It's a polynomial, right?
Yes.
This is eval 1, right? This is eval 2. And this is eval output. Right? How are we going to get, like, if we evaluate just these guys, we're just going to, if I evaluate this guy, I'm going to get 1. If I evaluate this guy, I'm going to get this add, right? 0 1. I'm going to get 1, right? So I'm going to basically get 2.
But yeah, okay, so generally the way I was thinking about it was that with our mod and add,
Okay.
yeah, right? It's not like we're going to add it like this, but we're looking for a polynomial, right? That will present, let's say, about
layer
1,
1.
about 1 layer 1, right? So it's going to be that we're going to write our mod, add, not necessarily mod and add, but those figures, we will have a polynomial of 1, 2, 3, 4, 5,
But
6, 7.
even this, sorry, let me just, like, we need a polynomial f of this a, b, c, d, e, f, g, h. Right? Should be equal to something. So if this is what we're passing into the polynomial, we can't get this, right? Because anything that is here is what will be here. Right? This will be 0, 0, 0, 0, 0, 0, 0, 0, 1. Right?
Why 0, 0? Why 0 is different?
Because we want a polynomial, right?
Mm-hmm.
Such that if we evaluate it at any of these valid points, we are going to get the answer.
Yeah.
So this is what we are passing into the polynomial.
If that is A, B, C, D, E, F, G, H.
Yes, it's A, B, C, D, E, F, G, H.
Yes.
Right? And this one you're saying is equal to more.
No, I'm not saying it's equals to more now. It's not necessarily equals to more. I'm thinking about it in the evaluation form, to be honest.
Okay.
More like.
So everybody, are we following?
Yeah.
So I'm thinking about it in the evaluation form. More like we have 8 variables. This is 8. If this is to which is 8, right? Then more like we have 8 variables. Then 0, 0, 0, 0, 0, 0, 0, 0, 1 equals 15.
Okay, so we're looking for that one polynomial,
Mm-hmm.
right? Let's say for anything we pass in here, that's what, like, the way we're passing it is the way we're distributing it in the polynomial. So this is A, B, C, D, E, F, G, H, right? Plus add A, B, C, D, E, F, G, H. So this is basically the polynomial we're looking for. It's close, it's not complete. But we want a situation where if we pass in f of 0, 0, 0, 0, 0, 0, 0, 1, we are going to get more 0, 0, 0, 0, 0, 0, 0, 1 plus add 0, 0, 0, 0, 0, 0, 0, 1, right?
Yes.
But then this should be equal to the answer we are expecting, which is 15. Exactly, which is 15.
So we know that, we basically know that add for 0, 0 is 0 now. It evaluates to 0.
Now add for 0, 0, okay, yes, it evaluates to
It
0.
evaluates to 0. So technically we are just
So
saying
this-
that the f of that 0, 0 is basically the mole of, I don't know if you get my point. So that means, like, it's basically saying the one is turned on.
Yeah, so this will go off, right?
Yes.
And turn to 0, but this will turn to 1,
1.
right?
Yes.
So if we do this addition, what we are going to get is 1,
Mm.
not 15.
Not, oh, the value, right?
Yes.
What if we do the,
Is it making sense?
what if we take those?
Wait.
Okay,
Sorry.
sorry.
I know, if I say don't the enter,
Sorry.
but okay. So does everybody understand what we're trying to do? So let me go over it again. We're trying to get, we know we've been able to define a polynomial to get the gates, right? Which is basically the small and the add, right? And we also said that these things can also be considered polynomials, right? Did we?
Yes, we did.
We said these things can also be considered polynomials, right? Good. So what I'm trying to say is that we're trying to get a polynomial such that if we evaluate that polynomial at a valid gate, like say this f of this, right? If we evaluate it as 0, 0, 0, 0, 0, 0, 0, 1, we are going to get 15, like this polynomial now. If we evaluate it at that valid point, we are going to get 15. If we evaluate it as 0, 1, 0, 1, 0, 0, 1, 1, we are going to get, what are we going to get? 10. If we evaluate it at 1, 0, 1, 0, 0, 1, 0, 1, we are going to get 8. And if we evaluate it at 1, 1, 1, 1, 0, 1, 1, 1, we are going to get 43. We need just one polynomial f of right? But now we need to construct that polynomial, right? How are we going to construct it such
So the
that
polynomial we need not a formula.
what is what's the definition of the formula? And
My definition of a formula is y1 plus y plus r into y2 minus y1. That's my definition of formula.
yeah, that's a
Why-
polynomial too, right?
That's why I'm trying to get that distinction. Like, is it we are looking for that array of points?
No,
or
just think of
we are
this
looking for
like
that combination that we can pass those points into and get that result.
see for now, like just think of it as a polynomial. Like you can think of the whole polynomial this thing as a black box, right? If you want to, you people have already implemented polynomial, right? So if you want to evaluate that polynomial now, you're just going to be calling those values. You're not necessarily thinking of the evaluation form and how it's going to pay again, right? Because you already have a function that does all that for you. You get, so you can think of polynomial as a black box, right? All you just need to do is like when I pass in these values into the polynomial, I should get this, right? The implementation details you guys have already implemented, and you have the polynomial already, so you can just black box it.
Question.
Okay.
We are assuming that the summation of the second layer, or the first layer one now, is going to equal to the summation of that polynomial over the hypercube, right? And so, why don't you write the full 5 variable Boolean hypercube and equate it?
And equate it. Yeah, but the polynomial is not complete now.
It's complete now. Those are our
Is it
evaluation
complete?
points. That middle layer is our evaluation point, right?
This one.
No, like I mean on the tree. That middle layer of 15, 10.
This one?
10. Yes.
Yeah,
that
it's our
middle layer
evaluation.
are our evaluation points, right?
Yeah.
So since they are our evaluation
Wait,
points.
they are evaluation points or they are the values that we get when we evaluate.
Yes, that's what it means. Don't worry. That's
Yeah.
what
But I get what they are not our evaluation. Our evaluation points are actually like
it
0,
means.
0.
Yeah.
Yeah.
But that's what it means.
Yeah, but I get
So basically, that's 15 there.
yes.
Right? And we know that 15 at the point on the Boolean hypercube when A is 0, B is 0, C is 0, D is it? Yeah, D is 0, E is 0, F is 0. G sharp ends at 1 is equals to
See,
15.
think of it with respect to the input layer.
Okay.
You're making an attempt, but you're thinking of it with respect to the output layer. Think of it with respect to the input layer.
What
Can you
if?
multiply
Sorry.
this?
Yes, you can.
Like 3.
Eh?
Where you have 1, for example.
Yeah.
Share there is like 3 bar. So like 3 times 1.
Sorry, which?
Like the hand parts.
Okay.
But multiply by go down.
Down. Oh,
Four,
okay.
five. Yeah, for the first parts, where you have 3 and 5.
Yes, 3 and
I
5.
think that's an evaluation.
Yeah, there's a polynomial, right?
Yes.
Uh-huh. And it's the evaluation of a polynomial.
At that point.
Yeah, at that point. Right?
So
So
you're saying
like-
the mod of that one gives you 1. The mod of 3 and 5 there gives you 1. Like of
Yes.
0, 0, 0, blah, 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 gives you 1.
Yes.
What's that part?
Wait, the mole of 3.
Of 0, 0, 0, 0, 0, 0, 1.
Wait, we have this eval input polynomial, right? If we evaluate this eval input polynomial at 0, 0, 0, we are going to get 3.
Yes.
If we evaluate this eval input polynomial at 0, 0, 1, we are going to get 5.
Yeah.
If we multiply
But
the two of them, we are going to get 15. Right? Okay. So what happened?
Wait, I mean,
So
So if we're bound at 0, 0, we get 5.
Like we said, you people said, right? Yes, yes. That you can think of this
As a polynomial.
as a polynomial, right? And that polynomial, if you evaluate it at 0, 0, 0, you're going to get 3, right? If you evaluate it at 0, 0, 1, you're going to get 5, right? Then if you multiply them together, you're going to get 15, right? Okay. That's what people said now. I just repeated what people said.
It's basically like so since the layer 0 basically our inputs are already displayed in like evaluation form. Alright. So like he said, when we see, since we know like the addition bit basically like evaluates to 0 since it's not turned on in the display. So our focus is on like the more parts, right?
Yeah. So is everybody following? Huh? Sorry, when he finishes, I'll go over what he said. Like everybody is just trying to contribute, right? So people should not like just sit back and also try, like when somebody makes a contribution, you may be able to pick something from what that person said and expand on it, right? So when somebody is trying to make a contribution, also like pay attention. Like I'm basically just pushing you people in the direction, right? Which I'm not supposed. You people actually went to like, actually figure it out. But I'm pushing people in the direction, right? And you people are actually making good progress, right? So just pay attention to him. So when he finishes, then you can ask a question. I can reiterate what he said. Okay, continue.
Okay, so I was saying that like since we know the addition basis like evaluating 0, our focus is on the multiplication part, right?
Yes.
And if you look at like the layer 0 evaluation form representation,
Okay.
when we have like 0, 0, 0, that's for C, D, and E,
Mm-hmm.
right? We know that points to 3.
C, D, and E, that's this guy.
Yeah, you know AB is for the output. Yeah, exactly.
Yes.
So C, D, and E is basically for like the first input in layer 0.
Okay.
So if we kind of like look for the value at that point in layer 0, we see that A3 is there.
Uh-huh.
And then if you are looking at FGH,
Okay.
which is 0, 0, 1,
Mm-hmm.
and we look for the value at that point at layer 0 as well, we see that we get 5.
Mm-hmm.
Now, you said we could multiply. You said
Yes.
we could multiply.
Mm-hmm.
So if AB, which is 0, 0, we know that like for layer 1, 0, 0 is basically like turned on in our layer 1.
Uh-huh.
I think we can
Should I reduce this to just ABC, so that like we
Okay,
know
yes.
A is the output,
Yes.
B is the left,
yeah,
C is the right.
Yeah, you can do that.
Is it okay with everybody?
Yeah.
And do we understand? Like if I reduce it, do we understand that it's
So
still?
my explanation is, what I was thinking was actually, I don't know, because actually I have the zeros and the ones and stuff. I don't, but then you can still use for the purpose of explanations.
Okay, so basically I'm just reducing this to A, right, B, and C, right?
Yeah.
A is equal to AB, right? B is equal to C, D, E, right? And C is equal to F, G, H. Does it make sense?
Yeah.
So where A is the output, right? B is the
Yeah.
left, C is the right,
Okay.
right? It's still the same thing. But I just reduce the number of variables.
So I was saying like if you look at B and C, they evaluate to both 3 and 5 in our layer 0
Yeah.
in evaluation form, and A which evaluates to 0, A which is 0 0 basically.
Yeah.
And we know that with the more value stored on, like that gate is stored on layer 2. So if I basically multiply like that's like 1, 3 and 5, I should get 15. And for add, like 0 0 there, sorry 0 0 there for add in layer 1
Yeah.
evaluates to 0, right?
Yeah. Sorry, this was like just a wrong this thing that so let me just clean it up so that it doesn't confuse us. I mean, let me take it up so that we can also like be seeing. Sorry. So that we can be seeing the tree basically. Okay. Is this okay?
Yes. So I'm thinking we are basically multiplying. That's why, like for both addition or multiplication, I think we are multiplying what the value of the gate is, whether it's 0 or 1, with the operation of those two. I don't, like I'm speculating now.
Like I was thinking the same.
So if
What's the basis? Like to say okay, I'm multiplying.
that's what I'm saying, I'm just speculating, but there's no basis for it.
Except maybe there's some special, like that output has some special, maybe when it's 0 0 it's add, or when it's 0
No, like
No, it's based on this example.
like this model already does that, right? This model already does that. Like if you pass in 0 0 0 0 0 0 0 1, mol will return 1, add will return 0. So anything we multiply with add is basically turning to
Yes, that's
just like
to
that's what
0.
I'm saying,
Yes,
just
that's
like
what you're
that
saying.
basis,
Yeah. So that's what you're saying, right? So now we've gotten 1 from the mole, right? But what are we expecting our output to be? We expect our output to be 15, right? And 15 is the multiplication of 3 and 5, right?
That's the evaluation.
Which is like
B and C.
B and C,
Yes.
right? So what I'm trying to say is that this formula is still lacking something,
Right.
right?
You mean the word like
Is it lacking like an expression?
It's lacking an expression.
Okay.
This formula, can we try it with if we're
Can we
looking
dis-
at addition?
Okay.
Yeah.
So if we're
from
looking
there
at
we can get like what it's lacking.
So if we're looking at addition, let's say for this gate, right?
Yeah.
That will be, we want the output of gate 0 1.
Yeah.
That output is basically telling us that like we want the final result to be 10,
Yes.
right? Okay. So 0 1, this is 0 1 0, right?
Yeah.
This is 0 1 1, right? So this is addition.
Yeah.
If we evaluate this more,
I will still using more for addition. Alright, yeah, continue.
okay. So if we evaluate at 0 1, 0 1 0, 0 1 1, and 0 1, 0 1 0, 0 1 1. Because this is what we're passing in, like A, B, C, D.
Yeah.
So you get
This one should give us, the more should give us 0.
more will give us 0, right?
Yes.
So add is what will remain, right?
So can we look at what is the
We're expecting the output to be 10.
right?
Yes.
So is there a way that the identity element of multiplication and addition come in here? Because
I think I'll say something.
okay.
So I'm thinking of it in like Lagrange form basically.
Okay.
So let's say we have something like y1, y2 for example.
Mm-hmm.
Y1 would be like the evaluation
Why am I
A.
smiling? Okay.
So y1 would basically be like the number at a specific index. Let's say left index.
Mhm.
Y2 would be the number at like the right index, right?
Mm-hmm.
So since we know that whatever we have in mod or add evaluates to either 0 or 1.
Yeah.
So the part that we want to be 1 basically can be something like, so if it's mod in our case, right?
Yes.
It will be y1 dot y2, right?
Mhm.
Times mod.
Okay.
Then we have plus y1 plus y2 times add.
Actually. Actually, like, he has gotten it, but maybe not all of us understand, right? So let's go through it, right? So we've gotten to this point, right? We know if we pass in anything we're passing in, we are distributing it between mol and add, right? Because it's variable for variable. Makes sense, right? And we know that there is no more gate, so this mol will basically equate to 0. There's an add gate, add will equate to 1, right? So we're missing some expressions. When we say more, we actually mean like multiplication, right? But there must be two things we want to multiply, right? One thing we would have done is like put 3 here and put 5 here, and then this is a more, right? So that when we multiply it with, okay, sorry. So one thing we would have done is like more 0 1 0 1 0 0 1 1, right? And we multiply it with say 3, but this one is 10, right? That is 7 and 3. Multiply it with 7 times 3, right? And then we add at 0 1 0 1 0 0 1 1, right? And we multiply this one with 7 plus 3, right? So 7 times 3 is 21, but this is a mod operation, so this will basically render this guy 0, right? Then this add will return 1, right? Times 7 plus 3, which is 10, which will be equal to 10, which is what we are expecting, right? But now we are dealing with concrete values, right? We are dealing with concrete values. Let's clean it out. Like this for the add case. Let's do that previous case, which was the more case. Do we understand this?
Yes.
We understand, right? Rahima? Are you sure? Okay, so let's do it for that previous case, right? Sorry. So for that previous case, what were we expecting? we're expecting 15, right? So 0, 0, 0, 0, 0, 0, 0, 1. So that's 0, 0, 0, 0, 0, 0, 0, 1, right? It should be equal to still our mole, right? Mole at 0, 0, 0, 0, 0, 0, 0, 1, right? Times, that was 3 and 5. 3 times 5, right? Plus add at 0, 0, 0, 0, 0, 0, 0, 1 times 3 plus 5. Does it make sense? So, in this case, it's a more gate that exists there, right? So this more will return 1, right? 1 times 3 times 5 is 15, right? Add returns 0. So basically everything here is 0, right? So basically when we add like 15 plus 0, we get 15, right? And what were we expecting? We were expecting 15. Does that make sense? Are we sure?
Yes.
But now we're dealing with concrete values, right? We need it to actually be a polynomial. And we can remember that, like I've been hammering this. You see people that said, though, it's not me that said, that this guy is a polynomial, right? And this guy is a polynomial too.
Which guy is that?
I think you change the ink.
Oh, okay. But this one will be clear. This okay?
Yeah.
So we said this guy is a polynomial, right? And now if we evaluate this polynomial at 0, 0, 0, we are going to get 3. If we evaluate this polynomial at 0, 0, 1, we are going to get 5. Right? Good. So instead of putting these concrete values here, right, why don't we just replace him, right, with why don't we just replace him with so why don't we just replace him with f, right, evaluated at, what is that? This was A, this was B, this was C, right? Evaluated at B, right? Times F evaluated at C. Does it make sense? This is a more, right?
Yeah.
So this operation has to be like a more, right? So we have F evaluated at B, which is basically this point, right? Times F evaluated at C, which is basically this point, right? And we are going to do the same thing here. This is F evaluated at B, where this F is this polynomial, right? The eval input polynomial. Is it making sense?
Yeah.
Maybe eval inputs right? Then this will be plus, right? Evaluated at C. So if this guy zeroes out, like everything zeroes out, right? Then we evaluate a value input at B times a value input at C, which will give us like 3. This guy should be equal to 3. This guy should be equal to 5, right? When we multiply it, we get 15, right? In this other case, right, is the addition that will trigger, and this 0, 1, 0, right? Evaluating this guy at 0, 1, 0 will give us 7, right? And evaluating at 0, 1, 1 will give us 3. So when we add the both of them, it's going to give us 10. Meanwhile, the mole will be cancelled out. I don't know if it makes sense.
Yeah, it does. So, this mall and this art, right? You know, from what we have now, we are the ones we can see the circuit, and that's from where we're able to tell that, okay, at this point mall is 0, and at this point mall is add is 0, and where add is present, add is so. Like, how do we tell, like, programmatically where mall is 0 and 1, like the same way we have check 0, check 1. So how I'm thinking that we have something like check mall or check add. So how are we going to know, like, because this is like we are seeing this thing with our eyes. So, but if we want to check this thing like programmatically, like how do we tell when, okay, mall is 0 or 1 and when add is 0 or 1, like, so
Okay.
so we know what to now use to multiply with the rest of the guys to know what to zero out and what to remain.
You know, like, let's go back to this guy. Right. Add polynomial. Depending, we're the ones, like, we know our circuit definition. Right. So since we know our circuit definition, we can generate this add polynomial from the circuit. Right? We can generate this add polynomial from the circuit. This add polynomial is a polynomial that if we evaluate that where we're supposed to have an add gate, we should get a 1, right? But if we evaluate at any other place that we're not supposed to have an add gate, we're going to get a 0. Is it difficult to create a polynomial? Like, it's basically going to be like in the evaluation form, right? It's basically going to be a polynomial, which is a vec of field elements, right? With all zeros except but 1 at the places where we have a valid gate.
Okay, that polynomial will just represent
the
circuit.
The add.
Yes, and
the mall will also have its own for a particular layer. Each layer is going to have its own. Like, it's I know, like, it's beginning to look like a lot, right? It's beginning to look like a lot, and I understand.
You know that x minus 1 into x minus 2 all over x minus, that is basically a polynomial.
Yeah.
That is like zeroing out something and all.
Like, you don't even need to think of it to that level again per se. We are just evaluating the add polynomial and we are getting a value which is 1 if we evaluate it at a place where it has a valid gate, right?
I understand that when we that add polynomial, so we can have like a so there is a add polynomial for a particular layer and there's a more polynomial for a particular layer, right?
Yeah.
So
Like each layer
yes,
has both an add and a more polynomial
that is unique to that layer.
that is unique to that layer.
Alright, got that. So now, you know, before we generated that polynomial visually here, we have already seen the circuit, right? So that means from any circuit we are going to generate or we are going to come up with, from the circuit we should be able to create a polynomial like in form of an array that represents the add and mod for each layer. So we can have something like add poly layer 0 and more poly layer 0. Then we have for layer 1, 2, we have for, so depending on the number of layers that that circuit have, so we have those guys for each of the layers. You're not
Okay. Like based on your circuit,
yeah.
right? You're basically going to be the one that will write your circuit. You get. And based on the circuit, you are going to basically know like the positions where each gate is.
Okay. So like in the process of preparing my circuit, I will be the same person to prepare those stuffs too, like the polynomial as well. That the setup now for everything.
Like that information will already be in the circuit and you'll be able to get it from the circuit. Like for the add and the more, right?
But we'll learn it when we start creating circuit.
Yeah.
No problem.
Okay. Like does everything make sense up to this point? Are we sure? Huh? Okay. Which one? Okay, yeah, that's this one.
Yeah, like I'm just saying that I have this question I had earlier. Is it that F, A, B, C,
Yeah.
if you have more operators, you would have
Like if you have more gates,
more gates here.
yeah,
You
so
have more of that plus add on then plus maybe subtractions on. Don't even get what I mean.
okay, like if you have like outside addition and multiplication,
Yeah.
yes. If you had like a division gate or a multiplication gate or maybe any other gate, like you're still going to have you have more of these times like it will basically look like something like mod of, let's say, A, B, C, right, times what do we call that now, as for the eval poly, let's just say eval poly, right, of B times eval poly of C, right, plus add A, B, C times eval poly of B plus eval poly of C, right, plus, let's say it's a division gate, you have maybe a div A, B, C times eval poly of B divided by eval poly of C, right? So each operation is going to have its own polynomial. Okay, good. Each operation is going to have its own polynomial. That is because this is the evaluation polynomial. This is the evaluation polynomial, right? Which is this polynomial. So which is this polynomial, right? So when we evaluate it, that is when we are going to have this concrete, like this value, say that 3 or 5. Normally that polynomial will just give us maybe 1, right? Which is the evaluation of this small poly. Like if we don't include this part, like all of them, like if we don't include this part, right, then this polynomial is always only going to be returning either a 0 or a 1, because this small poly actually returns like a 1 or a 0, depending on if we're passing in a valid multiplication gate, and the add too, if we're passing in a valid addition gate. When I say valid addition gate, do you know what I mean?
Sorry, excuse me. I know that at the initial point we're trying to do where there's a plus, that's add poly should evaluate to 1.
Yes. Like, for example, there's a plus here now, right? So if we evaluate the polynomial as 0, 0, 0, 0, 1, we're expected to get a 1, right? If we don't have this other parts,
Sorry, if you evaluate was at 0, 0, 0.
the add poly for that layer. Okay, should we take a break? Let's take like a 5 or a 10 minutes break. Huh? Wait, what is the time? It's normally 3. What is the normal time? Normal time is 3 now. We'll still go through everything tomorrow. So should we take that break? Huh? Like let everybody just stretch a bit.
Yes.
You get. Okay. So we're talking about the add polynomial, right? And does everybody remember how we got the add polynomial? Yep. For each layer.
The output and the same case. then if it is present, anyone that is present for that layer is going to be 1. Anyone that is not present will be 0 for each input and output.
Okay, so say for this layer now, right?
Yes.
The output, which is 0, 1, right? And the input, which is 0, 1, 0, right?
Yes.
And 0, 1, 1, right?
The result is going to be
Because there is a valid,
present, is valid.
yes.
But if for the combination, the addition gate is going to be 0 because it's not a 6.
For which of the combinations? Sorry.
I mean 0, 0, 0, 0, 0, 1 and output 0, 0 is going to be 0 for addition.
Okay, yes, it's going to be 0 for addition. Yes.
Or 1 for multiplication.
Yes, 1 for multiplication. Right. So, does that make sense?
Yeah.
Sure?
Yes.
Rahima? Does it make sense?
I wasn't listening.
Right, sure. Okay. Well, I know you have to leave at some point, right?
Yeah.
But where did you?
You already like got the whole zeroing and
Zeroing out.
yeah.
Right. I like have I mentioned the eval part?
Yes, yes, yes.
Okay, this part.
Yeah, we did all of those examples.
Okay. So I think let me copy this guy and let's okay. So we said we are trying to get a polynomial, right? Such that if we evaluate that polynomial at a valid set of gates, we are going to get the expected result we wanted to get, right? Did what I say just make sense? That like what I said just now makes sense?
No.
Huh?
No, I
It
didn't.
didn't, right? So, like, we know this is a gate. It's basically an operation. So this is a gate. It's an operation, right? And we want a situation where, like, we want to generate a polynomial. Let's say f of, each gate takes in inputs, 2 inputs for now, like based on what we are defining. It takes in 2 inputs and gives out an output, right? So let's say that output is A, right? And the input is B for the left and C for the right, right? I want a polynomial that, if we evaluate it at the said label, right, the correct label, we are going to get the answer depending on the operation of that gate. So let's say here we have a multiplication gate, right? And for this multiplication gate, the label of the output is 0, 0, right? So that means A is equal to 0, 0, right? the level of the left input is 0, 0, 0. So that's B equal to 0, 0, 0, and C equal to 0, 0, 1. Right?
Yeah.
0, 0, 1. So we want a situation where if we pass in these values to this polynomial, we are going to get 15. We should get 15. Right? And then, say if we pass in, okay, let's just finish this one first. That we maybe do for the addition gate. Right. So, in order to get this polynomial, we've already talked about how to get the add polynomial, right? Can we remember how to get the add polynomial? Okay. So for each layer, we know there are two operations. Like for this layer, we have a mod operation, we have an add operation, a mod, and an add. But they are basically just two operations, multiplication and addition, right? So we need a polynomial for each of them. Like we need a polynomial for multiplication, and we need a polynomial for addition, right? And we want a situation where if we pass in the right label for, let's say, for the multiplication polynomial, if we pass in the right label for the gate, for that multiplication gate, we are going to get 1. Right? So in this case, let me just take this off. So this is, we want a multiplication operation or a multiplication polynomial, right? And an addition polynomial, right? It takes in an output A and two inputs B, C. The both of them, right? Does it make sense up to this point? Sure? It does, right? Does it? Okay. So, if we say A equal to 0, 0, which is the output, right? You know, A is the output, B is the left input, C is the right input. So if we say A equal to 0, 0, for now we're focusing on this layer, right? Layer 1. If we say A equal to 0, 0, we're basically talking of this gate, right? Because it's only this gate that has the output with the label 0, 0. If we say A is equal to 1, 1, which gate are we talking about? This last one, right? Which is this gate. Because it's only it that has the output label of 1, 1. Right? So once we have picked an output gate, there is only let's say one set of input values that can give us the output gate. That set consists of B and C, right? Only one set of B and one set of C, that when we combine it, is going to give us the output gate. Yeah. So for when we say 1, 1, the only values of B and C that will give us this 1, 1 is where B is. What is that? 1, 1, 0, right? And where C is 1, 1, 1. Right? So this is the only place where, like when we're talking about this gate in particular, this is the only combination that forms a valid gate. Right? and that gate can be an addition or a multiplication gate, but in this case it's an addition gate, right? That means in our addition polynomial, we want this polynomial to be a polynomial that if we evaluate at, let's say if we evaluate at a equal to 1 1, b 1 1 0, c 1 1 1, we are going to get 1, meaning yes, there is a gate here and it's an addition gate. It's the addition polynomial. So if we evaluate that addition polynomial at any point and we get 1, it means that there is a valid addition gate at that point. Does that make sense? So we have, let's say, at for this one now, 1 1, right? 1 1 0, 1 1 1, which is A, B, and C, right? And this should give us a 1 because there is a valid addition gate here. Still at this same point, if we evaluate the multiplication poly at this same point, 1 1, 1 1 0, 1 1 1, we're expected to get a 0. Why? Because, like, although there is a valid gate at this point, it is not a multiplication gate. Right? Does it make sense? Does it make sense? Okay. So basically that's what we are trying to achieve. We want to get like an addition polynomial that when we evaluate that polynomial at any valid set of points, we are going to get a 1. So let's look at this again. There are two addition gates, right? This and this, right? Right? So if we evaluate this add at, since this is an addition gate, if we evaluate it at 1 1, 1 1 0, 1 1 1, we are going to get a 1 because there's a valid addition gate there. If we also evaluate it at add 0 1, which is the output, 0 1 0, and 0 1 1, we also want to get a 1, right? Because that's a valid addition gate, right? But any other place we evaluate this add polynomial at, we will expect to get a 0 because there is no other place that we have a valid addition gate aside these two places. Does that make sense? So for the multiplication, we have two multiplication gates. We are still basically trying to achieve the same thing. For the multiplication polynomial, if we evaluate it at a valid combination of labels, we expect to get 1 if there is a if there's a multiplication gate there, right? So if we evaluate the multiplication polynomial at 0 0 0 0 0 0 0 1, what do we expect to get?
1.
What do we expect to get? 1? It's a lie, 0.
Because the length, you have to put an wait, is that more?
Yes, it's small.
You guys.
Okay. So it's small. Yeah.
Okay, it's like a rapper keep something. Like 0 and 1 for 1 for addition, 0 for.
Yeah, like, but that is like the output, right? But now, like, I'm talking of like the inputs, right? So you can remember that this 0, 0 is A, right? Which is meant to be the output. This 0, 0, 0 is B, right? And this 0, 0, 1 is C. So now we are going to check as 0, 0. Okay, this is 0, 0, right? What is the left gate? Oh, sorry, what is the left input? 0, 0, 0, right? 0, 0, 0. And what is the right input? 0, 0, 1, right? So if we evaluate, and this is a multiplication gate, right? It's not a multiplication gate. It's a multiplication gate, right? So if we evaluate this multiplication polynomial at this point, since there's a valid multiplication gate there, we're supposed to get 1 as an output. I said 0 just to confuse you get. So. Okay, so that's a 1, right? So tell me another place where we expect to get a 1 if we evaluate this small polynomial.
1 0 as
1 0
as
and
1 0 0 as B.
okay,
1 0 1 as C.
1 0 1 as C. Is this not a 0? No, it's a 0 now. Check well.
It's not
Eh?
Yeah, that's from 3.
So 1 0 1 0 0 1 0 1, and it's a multiplication gate. Oh, so it's a 1. Oh, I did not know. It's a 1. It's a valid gate, right? Makes sense, right? Frankly, it's a more gate. Makes sense, right? Okay, so does this make sense up to this point? So we're trying to generate a polynomial, right? F of ABC, right? Such that if we evaluate it at the right set of values, we are going to get the expected output that we would have gotten if we evaluated the circuit. So basically, okay, so we're trying to get a polynomial, right? That if we evaluate it at f of a, b, c, we are going to get the expected output, right? So basically, let's forget about the inputs now, right? If we evaluate it at, let's say, still for this layer, right? Still for this layer, if we evaluate it at 0 0, right? Let's forget about B and C, right? What are we expected to get? We want to get 15, right? Because that output means we are just picking a value from the evaluation, for this evaluation like polynomial, right? You can remember how we got this polynomial. Oh, sorry.
Just hit your break. It will happen in the background.
Will it happen in the background?
Yeah, it's in the background. Yeah.
But you have to restart.
Let's not. I
You can
beg.
upgrade later.
Let's not risk it. Before we see that Microsoft blue screen, we get. So, so want to get a polynomial where this is the output, right? And fixing A means we want like the output gate to be 0, 0 basically, right? So we're basically, according to this polynomial, we're expecting 15. For now, we've not filled in values for B and C yet, right? So we're expecting 15. If we pass in F, that's my son check the right time. I'm typing for myself, started saying something. Right? If we pass in F as 0, 1, BC, what are we expecting? 10, right? This is 0, 1, this is 10. F at 1, 0, BC, what are we expecting? 8, right? Is it making sense? Are we sure? F at 1, 1, BC, we're expecting 43, right? So we need a polynomial like this, right? But this partial evaluation. So if we want to represent like the full evaluation to get this correct value, that will be F of 0, 0. What is B? 0, 0, 0. 0, 0, 1 should be equal to 15. Right? This is F of 0, 1. What is B and C? 0, 1, 0, 0, 1, 1 should be equal to 10. Right? And F of 1, 0, 1, 0, 0, 1, 0, 1 should be equal to 8, right? And F of 1, 1, 1, 1, 0, 1, 1, 1 should be equal to 43. Is this making sense?
Yeah.
Does it make sense? Okay. So this is what we want to achieve. We know that like this is the polynomial. Normally they call it the W polynomial, right? If you have read like the Proust argument and ZK, they call it the W polynomial. So this is actually the W polynomial for layer 1, right? Which is this. Is it making sense? This and this are actually the same thing. Right? Like this and this is the same thing now, right? Is it not the same thing? It's the same thing, right? So basically what we're trying to get is this polynomial for layer 1. We want a polynomial that if we evaluate it at this, we're going to get 15. If we evaluate it at this, we're going to get 10. If we evaluate it at this, we're going to get 8. If we evaluate it at this, we're going to get 43. Right? If we evaluate it at any other place, it's not our business, right? But if we evaluate it at these places, we want to get these values. Is it making sense? So now let's focus on 1, right? Let's focus on this one. How can we generate this polynomial? Or let's just focus on like the general polynomial. Right? F of A, B, C. Right. And you know, like if we pick the output, we're basically forcing inputs. Because for this one now, if we pick this output of 0, 0, we are forcing 0, 0, 0, 0, 0, 1, right? If we evaluate this at 0, let's say 0, 1, 0, 0, 0, 1, it will give something totally different, right? Okay. So we already know how to get the more polynomial for each layer, right? Like for layer 1, we know how to get the add and the more polynomial for it. I know why I'm always going back to ask that question.
What do you mean by how to get?
That is basically the polynomial that if we evaluate it at the valid set of inputs, we are going to get 1 if it's a more gate, right? Like this more polynomial. And if we evaluate it at the valid set of inputs labels for the add, we are going to get a 1, like the add polynomial, which is like this one. Does it make sense? Hope I've not confused somebody. Okay, so what I'm just asking basically is that we know how to get, like for this layer 1, we know how to get the more polynomial and the add polynomial. And we know what the more polynomial and the add polynomial are supposed to do. Do we? Do we? Okay. Okay, so like based on that now, based on the more polynomial, A, B, C, right? And the add polynomial, right? What's remaining now is how to get, because these are the values we want when we evaluate at a valid point. Those are the values we want. So in order to get these values, let's say this is more for layer I, right? And add for layer I. We'll need to multiply it with, let's call it the W polynomial now, right? At the W polynomial evaluated at B, right? This is the mole operation times the W polynomial evaluated at C. Frankly. Okay. So we want to get a polynomial, right? F of ABC, such that if we evaluate it at 0, 0, 0, 0, 0, 0, 0, 1, we are going to get 15. Right? And we know that each layer is made up of both addition and multiplication gates. And we've talked about how to get the addition polynomial for each layer and the multiplication polynomial for each layer. Can you remember how we got the addition polynomial for each layer and the multiplication polynomial for each layer? Like for this particular layer now, can you remember how we got the addition polynomial for it and the multiplication polynomial for it? You can. Okay. So, like I said, we need a polynomial that if we evaluate it at a valid label, like for the more polynomial, we want a situation where if we evaluate it at the valid labels of a multiplication gate, we are going to get a 1. Yes, that's it. Makes sense, right? Yeah. So that's this more polynomial. Then for the add polynomial, if we evaluate it at a valid labels for an add gate, we are going to get a 1. So that's how we got this add polynomial, which is basically this small and this add. Right. So if we pass in ABC to this function, this small is either going to return a 0 or a 1, right? Add 2 also return a 0 or a 1, right? So the only way we can get like the
Sorry. When you say valid label for add gate and valid label for mod gate, are you talking about the 3 variables at the lower part, or what exactly are you referring to?
Yeah, both the outputs and the 3 variables at the left and the 3 variables at the right, because those are the things that define a gate, right? The output, the left input, and the right input.
So is it like you carry a kind of operation to test what sign it is, like maybe add it together to check if it gives the output, or multiply it to see if it gives the output?
Yeah, that's what like we're trying to, like that's the polynomial we're trying to develop.
Okay.
This f of ABC polynomial.
Yeah, no, I was actually like to get the multiplication, the mole and the add. And that's what I was trying to ask on.
Yeah, like if we evaluate the more polynomial at a valid label, when I say valid label, you understand what I mean, right?
Yeah, I understand.
Yeah. So if we evaluate the more polynomial at a valid label of a more gate,
yes,
we should get a 1. Right? So this is a more gate, right? This is a multiplication gate. And the valid label for this multiplication gate is 0, 0, 0, 0, 0, 0, 0, 1.
Yeah,
and this is another more gate.
yes, 1 0.
1, 0, 1, 0, 0, 1, 0, 1. So we want this more polynomial. If we evaluate it at any of these 2 valid labels, we are going to get a 1.
When you say evaluate now, are we using the normal partial evaluate?
So the normal full evaluate.
The normal full evaluate we have.
Yes, for that add for the more polynomial. Because full evaluation, we are setting concrete values for each of the variables.
Yeah. So now when we now evaluate it, when we use this point now to evaluate it, are they going to act like ABC for that particular polynomial?
Yes.
Okay, so the 0 acts like A.
Acts
The
as
0
A.
0
0 acts as B. Yeah, the 0
1
acts as C. Yes.
Got it.
Does it make sense? Okay. So this mol and this add, right? If we evaluate it at a valid, say for a valid mol gate, if you evaluate this polynomial at a valid mol gate, this mol will return 1, right? But the add will return 0.
Yeah.
So anything we multiply with the add will be zeroed out, right?
Yeah.
But anything we multiply with the mol, since the mol will return 1, then it's going to basically return this other side of the equation.
We are supposed to represent that. We're supposed to write WB plus W for the add part.
Yes, for the add part, I'm meant to write that. Plus WC.
So if you add more than two operations, if you add more than multiply and add, that means let's say we add minus as well, subtract. We also add it to.
Yeah, we're also going to have like a sub, right? A, B, C. And it's going to be W, B minus W, C.
But there's no subtraction.
Yes. That's if we had. Yes. Yeah. So, does this make sense? Are we sure? Please, are we sure? Okay. So if we evaluate it at a valid add gate, like valid label for an add gate, the mol will cancel out, right? Because mol will return 0, right? So the mol will cancel out, and the add will return 1. Then when we multiply it with WB plus WC, we are going to get the actual addition of those two values. Right? So what is this WB and WC? This W is a polynomial, right? And for this layer 1 is the polynomial of our input values. That's what that W polynomial is.
The W or the WC itself?
The W polynomial. This is W of X. We can evaluate it at any point. If we evaluate it at B, that is what to give us WB. If we evaluate it at C, that's what will give us WC. Right? But it's actually a polynomial, W of X. Right? Does it make sense?
Yes.
Are we sure? Sure. Sure. Huh?
But that's 15 now, for instance, was the evaluation at B and C, using B and C that got that 15. So why
using the valid B and C?
Yeah.
If it was just 0, 0, but B and C were not valid, we are not going to get 15, right? If B and C were not valid, we are not going to get 15.
Definitely.
Yeah, so it has to be valid for us to get 15. But do we agree that we understand what this W polynomial is? Is for this layer, right, is the evaluation, the input basically, right? For this other layer, the W polynomial will be the output of the previous layer, right? If we can remember, which is this. Right? For this next layer, this one is going to be our W polynomial. Yeah, 25 and 344.
So meaning the points are more like the W values.
Yeah, you can think of it that way. So which are like the evaluations of the circuit for that. Yeah. Okay, so does it make sense up to this point? Are we sure? It makes sense up to this point. Okay, so now we can see that if we think of this as W1, right? I will think of this as W0, right? We can see that we are basically forming a relationship between W1 and W0 based on this equation.
Yeah, layer.
Sorry,
Below the
I didn't
layers.
see, where did you write W1?
Sorry.
That means with the W1 we can get W2.
Yeah, that means with W1 we can get W2. And with W2 we can get W3.
And the higher
Yes.
we go, the lower the number, the set.
Yes, the smaller the set. We can see that based on that, like, let's call this one W0, right? Let's call this one W1. Let's call this one W2. Let's call this one W3. Right? What can we see basically? We can see that with that function, we have been able to form a relationship between W1 and W0. Do we agree?
Yeah.
Because if we evaluate this f of b c polynomial, like this f of a b c polynomial, if we evaluate it at 0 0, right, we are going to get 15, which is the evaluation of W1 at 0 0, right? If we evaluate it at this f of ABC, if we evaluate it as 0 1 and like the valid sets of labels,
Yeah,
we are going to get 10, right? Which is the evaluation of W1 at 0 1, right? If we evaluate it at 1 0, we are going to get 8, right? Right. For now, I'm just talking like evaluating like based on A, but we know like it has to be a valid gate. Like it has to be this valid combination for it to give us the correct value, right? And then if we evaluate it at 1 1 and like the corresponding valid set of labels, we are supposed to get 43. So we've been able to get the evaluation of this W1 polynomial over the Boolean hypercube by just evaluating that f of ABC at the set of valid labels, right? I don't know if it makes sense.
Yeah.
Are we sure?
Yeah, but then the question now comes that how do we now get the set of valid labels for a particular point? You know, we are not seeing the, except you see we are seeing the history. You know, we are just having the starting evaluation point, and then how do we now get the set of
Valid labels,
valid
right?
labels for a particular point?
So this set of valid labels is somewhere in the Boolean hypercube, right? Like this set of valid labels is somewhere in the Boolean hypercube,
Yes. Definitely.
right?
Definitely.
Do we agree?
Yes.
Okay. So that's basically where sum check comes in.
You know, in this case now, we just, okay, even say we want to assume random Boolean attributes and stuff to use for a set of valid labels. How do we get the points two of them will give to know that, okay, this is the point we are going to get? Let's put it like this. Now, the f of ABC should give us 1 at full evaluation.
Yes, f of ABC should give us
1.
No, is it giving
For
us
valid-
1?
For valid input.
No, f of ABC for a valid input is going to give us the answer. Like that is this 15, either 15 or 10 or 8 or 43.
Or I was thinking to get the mole of the addition.
No, that's inside f of ABC. That is where we have the mol and the add,
Yes.
right? That's where we have like this.
It is the mole of ABC that gives us 1.
Yes. Like if it's a valid label.
Yeah.
Yes.
So we have to now write a function for like the mole of, and then function for like the add of.
Yeah, that is basically this two, right? Like minus this part two. That's basically this mol and the add. Like are different functions. Each layer has an operation. Like each layer has 2 operations, right? Add and mol, right? And this is the mol for the layer, and this is the add for that layer. You get? So which is going to give us a 1 if, like, the mol is going to give us a 1 if it's a valid combination of mol gates, right? And then since it's a valid combination of mol gates, it will automatically select the corresponding values from the layer beneath, right?
Yes.
Since it's a valid set of mol gates, right? This 0, 0, 0, when we evaluate W0 at 0, 0, 0, we'll get 3. If we evaluate W0 at 0, 0, 1, we get 5.
Yes.
Then if we evaluate mol at 0, 0, 0, 0, 0, 0, 0, 1, we're going to get 1. So that 1 times 3 times 5, which is basically this, right? This 1 times 3 times 5. So this is what it's going to look like if we do f of 0, 0, 0, 0, 0, 0, 0, 1. It's going to be mol, right, at 0, 0, 0, 0, 0, 0, 0, 1 times w of 0, 0, 0, right, times w of 0, 0, 1, right, plus add,
The invalid part. Okay.
right,
Just
like,
finish it.
yeah, plus add 0, 0, 0, sorry, 0, 0, 0, 0, 0, 0, 0, 1 times w 000 plus W 001, right? So this is what it's going to look like. We're just passing in A, B, and C, but it's distributing it internally, right? Where this is A, this is B, this is C.
So my question, to restructure my question now. So my question now is, now we have the evaluation over the Boolean hypercube, and then definitely we have our 0000001 from there and stuff. So now we need that next evaluation point, which is 00, for instance, to be able to check
Of the next layer.
Yes, on the next layer, to be able to check if something is a mol or R, depending on whether it will give 1 or 0. And if we pass in a mol, like if we pass in a mol, it should give 1 for mol. And then if we pass in an add,
That's 1 for more internally here.
yes, like
Okay.
1 for mol. So we need that first point now, that's 00 now. So how do we get that first point? Now, we have this last two. How do we get the first point?
That will be the verifier's random challenge. But let's not get there first. So, basically how it happens is that the verifier will say, okay, for 00, we can think of it that way. For 00, which is the output, right?
Yeah.
Give me the corresponding evaluation, the correct evaluation. Like if the verifier say for 00, like this output now 00, give me the correct evaluation, which is meant to be 15, right? Based on the evaluation of the circuit, right, like based on the labeling of the circuit, what the prover now needs to do is this B and C, right, the verifier has already said let A be 00, so A 0000, right? So the prover puts the valid labels for B and C. And when the prover evaluates it, the prover is going to get 15, right? And tell the verifier, oh, the answer is 15. You get? But now, this thinking of it in the Boolean hypercube. Actually, the verifier actually samples a random challenge. Right? So the verifier will say, for gate 50, 100, give me the correct label. Like, if you want to think of it in this way, that's why they call the that's why they call it multilinear extension. So good and fine, we define the polynomial over zeros and ones, but we can evaluate it at any point.
Yeah. You said the verifier is going to sample the random variable.
By ways. Okay. Yeah.
Alright, you said you said the verifier is going to sample a random challenge, which is going to give to the prover to like evaluate at let's say 00, right? Now
Wait, sorry. The verifier is going to sample a random challenge. Yes. And give the prover.
Yes.
So when the verifier samples a random challenge, I wanted us to understand this thing first before I talk about that, but let me just talk about it. Okay. So when the verifier samples a random challenge, the verifier basically replaces A here with that random challenge. Right? So if the random challenge is, for each of these variables, that has to be a random challenge. So for A, let's say the verifier samples 50.
no,
I think
Oh, yeah. Okay. I think it's connected. Okay. Right. Let me just be sure. Okay, so if the verifier samples say 50 and 9, right? So I basically say, okay, put 50 here and 9 here, right? That will immediately mean, sorry, are we following? That will immediately mean that here it will be 50 and here will be 9, here will be 50, here will be 9. Then the prover is expected to get the valid labels that will give the correct sum.
Okay. That will work because I was thinking because if the verifier is the one that gives the values, right? The initial value,
The input value.
this thing to the prover, and the prover evaluates. So I was like thinking if the verifier is like giving the prover sampling random challenge to the prover at a particular point, it's not going to yield back the initial values. So but your explanation makes sense now.
Okay.
Also, how does the verifier know what to expect? Because he's giving a random challenge for these 2 points that would have to be made with that point is the random challenge to get an output. So how will he know what to expect to be able to certify that the verifier is not lying?
That the prover is not lying, right?
Yeah, that the prover is not lying.
So, like I was saying, that's where like some check comes into play, right? So we're proving a claim on layer WI against a claim on the input layer W0. So it's kind of like a reduction, right? We have a claim on this layer, right? And you're trying to prove that it's a claim on this layer.
So that means he has that already, that 15.
Who?
I mean the verifier.
The verifier does not need to have it. That is the beautiful thing about like GKR. Basically, the verifier doesn't even need to have all these intermediate values.
So how does he know? Like, what does he check it by?
The prover is going to perform like some check, right? I know some check, there is a claimed sum in some check.
Yes.
Yeah.
That's the initial claim sum.
Yeah. So that initial claim sum would actually encode that relationship. But we're going to get to that point.
I've started this is how the setting
Okay, so do we understand up to this point? Are we sure?
Yeah, tired.
That's not
No,
it.
that's 35. No.
Just one question.
Okay.
We stayed till 3 now.
Why
What's
is
5?
2 by 2?
Don't wipe us
Yeah,
out.
so my question is like, now, okay, I've gotten this right. You
Yeah.
said that for you to prove like those 2.00, if you give like the prover points 50 and 9 instead of 0 and 0, right? So the prover is supposed to provide valid points for B and C, or valid evaluation points for B and C that fits 50 and 9.
Yeah. So if you can remember, like in some check, right? If you can remember in some check, when the verifier samples a random challenge, right? The prover evaluates the polynomial at the random challenge, right? And gets a new polynomial, right? And that new polynomial now, the verifier, what does the verifier do? Or what does the prover do? The prover gets the claimed sum of that new polynomial and it returns a univariate polynomial. The verifier basically checks at 0 and 1, right? And then if it's valid, it accepts. So we are going to be using like some check, you get, to actually prove like that relationship between a layer and the layer beneath. Yeah. So I think it's 3 already, right? So no, we've not gotten to that point yet. We've not gotten to that point yet. Yes. So the goal is like to take it slowly, like let what we've said first marinate.
What you care about now is like
That's a question.
more.
Yeah, the add and the more. Does the add and the more make sense? And the W, does add, mol, and W make sense? Like what they are trying to achieve, how to generate them.
Achieve the goal for today.
Yes.
So the other one is extra.
That's a question.
Yeah, so
Just one wrong.
I want to, I don't know if maybe you can just give us like a picture of GKR. So that, like, you know, we know, let's just know the picture of GKR, like what it's all about. So with that picture of GKR, we'll be able to like find a way
5 seconds.
to
5 second picture.
Yes.
5 second picture. What's happening is, can you raise the let me see the input.
Not this kind of picture.
Wait, not that kind of thing, I know. So this is the input layer, right?
Yes.
This is what the verifier knows, right?
Yes.
The verifier trusts this.
Yes.
Because the verifier was the one that gave you this to
Yes.
evaluate circuit art.
Yes.
So the verifier trusts this.
Yes.
The rest, the verifier doesn't trust,
Yes.
right? So the prover is going to say that the answer is 8,600. It's going to make a statement here. You don't know whether that statement is true or not. Okay? So you're going to use some check to reduce that statement to another statement about this layer. Okay? So let's say the prover said W3 evaluated at 0 is 8,600. You're now going to do some math magic and you get a new statement that says W2 evaluated at 48 is equal to 925, right? But when you now reduce this to this statement, you can forget about this statement. Okay? If this statement is correct, then this statement is correct. You have done a full reduction. Does that make sense? Now you do that again, and you do that again. Until you get a claim about the inputs.
Yeah.
So at some point, the provider is going to say that the inputs evaluated at 725 is equal to 936. Now the verifier has this. The verifier can check that by themselves. And once they check that, it means that this other claim was correct, this other claim was correct, and this other claim was correct. Then you can take the output. Does that make sense?
Yeah, I was always imagining the verifier all fat guy that does not want to do anything at all.
Yeah, that's it.
He doesn't do anything. Yeah, he's still doing work.
No, he's not doing much.
And he's calculating, he's going down the level. So if there are like 1,000 levels, he will go down 1,000 steps.
It's not a lot.
Just
I know it's
Okay, so I think we can call it a day. Then we'll continue tomorrow.
Can drop this video now. Can drop it now. Okay. If possible. So that we will
Really?